Before there were cities, before there were books, before there was any name for what we do when we study the stars, there was simply the act of looking up. A person, somewhere, on a night without a moon, stepping away from the low firelight and tilting their head back. That is where this long, slow story begins. Not with a discovery, not with a sudden flash of understanding, but with a quiet gaze. The same gaze you can offer tonight, if you step outside, or even just look out a window at the dark. The sky at night is the oldest shared experience we have as human beings. It connects every culture, every century, every quiet watcher who ever lived. The same stars that are drifting above you right now, or waiting behind the clouds, are the stars that people watched thousands and thousands of years ago. The same slow turning, the same deep, dark quiet. When you look up on a clear night, away from the bright lights of streets and signs, you see a sky that would feel completely familiar to someone who lived 10,000 years ago. They would recognize the wide, dark bowl overhead. They would recognize the scattered points of light, some bright, some so faint you have to look slightly to the side to catch them. They would recognize the broad, misty band of the Milky Way, like a soft spill of spilled milk across the darkness. This was the first astronomy. No instruments, no calculations, just eyes and patience and the deep dark of a world without electric light. The first astronomers were anyone who sat still long enough to notice that the stars move, slowly and together, as if the whole sky is a great, quiet wheel. They noticed that certain bright points moved differently, wandering among the fixed stars. They noticed the changing face of the moon, growing from a thin curve to a full round disk and then shrinking back again. All of this was seen, and watched and remembered, long before anyone wrote a single word down. The earliest sky watchers did not need telescopes. A telescope is a beautiful tool, and we will come to its story later in this long, gentle walk. But for thousands and thousands of years, the only tool was the human eye, slowly adapting to the dark. After about 20 minutes in the dark, your eyes become much more sensitive. You can see fainter stars. You can see the soft glow of the Milky Way more clearly. This is a physical change that happens in your own body. A quiet adjustment that connects you directly to those ancient watchers. They sat in the dark and let their eyes grow wide and receptive, just as yours do. The patience required was immense. There was no hurry. There was no place to be. The sky turned at its own slow pace, and the watchers turned with it. This whole story, the long walk we are taking from those first quiet gazes to the great telescopes spinning in space right now, is a story of patient watching. It is not a story of sudden breakthroughs or dramatic shouts. It is a story of slow, careful attention passed down through generations, night after night after night. Think for a moment about one of the most basic ways people have always oriented themselves. Imagine standing in an open field, under a wide sky, with no map, no compass, no phone. How do you know which way you are facing? During the day, the sun gives a rough guide, rising in one direction and setting in the opposite. But at night, there is a quieter guide, a fixed point. In the northern sky, there is a star that seems to hardly move at all. It is called Polaris, or the North Star. It is not the brightest star in the sky, a common gentle misunderstanding, but it is a steady one. If you find it, you know where north is. You can find it by looking for a pattern of 7 stars that many people call the Big Dipper, which looks like a soup ladle or a plow. The 2 stars at the outer edge of the ladle's bowl point toward the North Star. For centuries, travelers and sailors and people walking home across dark fields have used this fixed point to guide them. It is a small, quiet anchor in the turning sky. The North Star sits almost directly above the Earth's North Pole, so as the Earth spins, all the other stars appear to wheel around it in slow, concentric circles. The North Star itself stays nearly still. This is a simple fact of perspective, a gentle trick of our moving planet. But knowing it, and relying on it, is one of the oldest and most calming pieces of knowledge a person can hold. Just knowing there is a fixed point, a steady light, can be a comfort in the dark. It was a comfort to people long ago, and it remains one now. The night sky offers these fixed points, these quiet certainties, in a world that often feels full of motion and noise. The patterns of the stars return each night, at roughly the same times each year. The ancient watchers learned these patterns intimately. They gave names to the groups of stars, the constellations. They told stories about them, passing the shapes and tales down from parent to child, from elder to younger. These stories were a way of remembering the sky, a kind of oral map. Every culture developed its own patterns, its own names, its own stories, laid upon the same canvas of stars. The stars themselves did not change, but the human imagination painted them with bears and hunters, with swans and scorpions, with creation tales and moral lessons. This was astronomy and storytelling woven together, a single fabric of understanding the world above and the world below. Looking up was a way of remembering who you were and where you came from. And there is a deep physical pleasure in simply looking, without needing to name or analyze. The act of letting your eyes wander across the darkness, from one faint point of light to another, is itself a slow, soothing rhythm. The stars do not demand anything of you. They do not flash or move suddenly. A shooting star, a meteor, is a rare and gentle exception, a brief streak of light that crosses the sky and is gone, leaving you wondering if you really saw it. Most of the time, the sky is a portrait of exquisite, profound stillness. The only movement is the grand, imperceptible turning of the entire dome, a movement so slow you cannot see it happening, but if you look away and then look back, you realize the stars have shifted their positions slightly. The whole sky is a clock, the oldest clock there is, and its hands move with a grace that no human clock can match. Watching it is like watching the breath of the world, inhaling the night, exhaling the day, a slow, steady pulse that has been beating since long before we were here and will beat long after. This is where we begin our slow walk, not with a textbook or a lecture, but with that simple, human act of looking up. The story of astronomy is, at its heart, the story of people standing in the dark and paying attention. It is a story of questions asked softly, over centuries. What are those lights? How do they move? What is our place among them? The answers came slowly, piece by piece, and often the answers only led to deeper questions. That is the nature of this story. It is not a straight line from ignorance to knowledge. It is a winding, gentle path, with many pauses, many quiet moments of simply watching. Every astronomer who ever lived, from the anonymous builders of stone circles to the physicists operating space telescopes today, started in the same place. They started by looking up at a dark sky and feeling a stir of curiosity, a sense of wonder that is not loud or shocking, but deep and quiet and slow burning. A feeling like recognizing a familiar face in a crowd. The sky is a familiar face. It has been looking down at us for the entire history of our species, a constant, silent companion. So as you lie here in the dark, let your mind drift upward. Picture a sky free of city lights, a sky so full of stars that the constellations are hard to pick out because there are so many points of light in between them. Imagine the soft, dusty glow of the Milky Way, stretching from one horizon to the other, a river of ancient light. Some of the stars you see are so far away that the light has been traveling toward you for hundreds, even thousands of years. You are seeing not the star as it is right now, but as it was when the light left it, long ago. You are looking directly into the past, just by tilting your head back and opening your eyes. There is a word for this, a calm and simple word, light time. It is not a complicated idea. It just means that light takes time to travel, and the farther away something is, the older the light we see from it. The light from the North Star that you might see tonight left that star around the time the printing press was being invented in Europe. The light from the faintest smudge you can see with your unaided eye, the Andromeda Galaxy, left that galaxy more than 2 million years ago, long before there were any humans on Earth to see it. When you look at the night sky, you are a time traveler in the gentlest possible way. The past is arriving at your eyes, moment by moment, photon by photon. This is not a dramatic revelation, it is simply a quiet, beautiful fact. And it is one that the earliest skywatchers could not have known, but they were looking at the same past light nonetheless. They were seeing the same photons, the same ancient messages, without yet knowing how old the messages were. We will walk through that unfolding knowledge together, step by gentle step. We will visit the ancient monuments built to track the sun and stars. We will visit the early astronomers in Babylon and Greece, in China and India and the Mayan lands. We will visit the great observatories of the Islamic Golden Age, where the old knowledge was preserved and deepened. We will see the slow, quiet shift from an Earth-centered cosmos to a sun-centered one. We will see the first telescopes, and then the larger ones, and then the ones that left Earth altogether. But all of that is ahead of us. For now we are simply here, at the beginning, in the dark, with the oldest view there is. The same view that has always been there, waiting for anyone who steps outside and looks up. The same view that will be there when this long, slow story reaches its end. The sky does not hurry, and neither, tonight, should we. Just breathe, and listen, and let the quiet turning of the stars above carry you, slowly and gently, toward rest. The sky is a familiar face. It has been looking down at us for the entire history of our species, a constant, silent companion. And because it is a familiar face, people have always tried to understand it, to mark its expressions, to predict its moods. The earliest attempts to do this, to reach out and touch the sky in some permanent way, are written not in books but in the landscape itself. They are written in stone and in earth, in the careful placement of enormous rocks and the cutting of precise ditches. These are the first astronomical records, though they record no words. They are the first observatories, though they hold no lenses. They are the places where the patient watching of the sky became something you could hold in your hands, something you could walk through, something built to last beyond a single human lifetime. Think of a place like Stonehenge, on the wide, windy Salisbury Plain in the south of England. It is a ring of standing stones, some of them more than 20 feet tall, set upright and capped with horizontal lintels, all arranged in a circle with a central horseshoe of even larger stones. It was built in stages over a very long time, starting around 5,000 years ago, which is to say around 3,000 years before the Common Era. The earliest work was not the stones themselves but a circular ditch and bank, with a ring of 56 pits that archaeologists call Aubrey holes. The great stones were brought later, from quarries many miles away. Some of the smaller stones, the blue stones, came from the Preseli Hills in Wales, more than 150 miles distant. How they were moved, without modern machines, is still a matter of careful study and quiet debate. The effort involved was enormous. It tells us that this place mattered deeply to the people who built it. And what was it built for? That is the question that hangs softly in the air around any ancient monument. The plain answer is that we do not know for certain. There are no written records from the builders of Stonehenge. They left no texts explaining their intentions. All we have is the stones themselves, their arrangement, and the patient, careful work of archaeologists and astronomers who have measured and aligned and considered. What they have found is that the stones are not placed randomly. The central axis of the monument, the line that runs through the center of the circle and out along a broad avenue, points toward the place on the horizon where the sun rises on the summer solstice, the longest day of the year. On that morning, if you stand in the right place inside the circle, you see the sun lift itself above a stone placed far outside the ring, the heel stone, and its first light shines directly into the heart of the monument. This alignment is precise. It is not an accident. Stonehenge, whatever else it may have been, was a way of marking the turning year, of anchoring the endless wheel of the seasons to a fixed point on the ground. but the exact purpose of Stonehenge remains debated by historians. It may have been a temple, it may have been a burial site, it may have been a place of healing or a calendar, or all of these things at once, its meaning shifting over the centuries as different generations added their own stones and their own understanding. The uncertainty is part of the calm. We can stand in the ruin and look at the stones and feel the weight of the not knowing. We can imagine the people gathering there on the shortest night of the year, watching the sun rise in a blaze of midsummer light, but we do not hear their voices, we do not know their prayers. The stones keep their own counsel, and that is all right. The quiet of Stonehenge is not an empty quiet. It is full of the questions we are still asking. What are those lights? How do they move? What is our place among them? The builders of Stonehenge were asking those same questions, and their answer was built in stone, a massive, silent, patient answer that still holds the sunrise today, 5,000 years later. Stonehenge is not alone. Across the world, ancient peoples built structures that reach toward the sky. In Ireland, a passage tomb called New Grange, older than Stonehenge by several centuries, has a narrow stone passage that is aligned with the sunrise on the winter solstice, the shortest day of the year. On that morning, a beam of light creeps slowly up the passage and illuminates the central chamber for a few precious minutes. In the Americas, there are mound structures and stone circles that track the movements of the sun and the moon. In the high desert of Peru, there are lines drawn in the earth, called the Nazca lines, that some researchers think are aligned with celestial bodies, though again, the exact purpose is not fully known. The same pattern emerges wherever we look. People in different times and different places, separated by oceans and centuries, all had the same impulse. They all looked at the sky and wanted to pin it down, to bring it to earth, to mark its rhythms in something more permanent than memory. Memory, however, was the first step. Before stone, there was spoken knowledge, passed from elder to child, and then, slowly, came writing. The oldest written star records that we know of come from a land between two rivers, the Tigris and the Euphrates, in what is now Iraq. This region, called Mesopotamia, was home to the Babylonian civilization. More than 3,000 years ago, Babylonian scribes began pressing wedge-shaped marks into soft clay tablets, using a stylus cut from a reed. The marks, which we call cuneiform, recorded many things: business deals, laws, letters, and quietly and carefully, the movements of the sky. The Babylonians watched the sky with a methodical patience that still speaks to us across all this time. They did not simply glance up and note that the moon was full. They recorded, night after night, the exact positions of the planets, the phases of the moon, the timing of eclipses. They compiled these records over generations. A scribe in the city of Babylon, perhaps sitting on the flat roof of a temple, would consult tablets that had been written by his grandfather and his grandfather's grandfather, and would add his own observations to the growing pile. This is the beginning of astronomy as a continuous, cumulative practice, not just one person looking up, but a whole culture building a shared record across time. These clay tablets survive today. They are hard and durable, baked either by the sun or by the fires that destroyed the cities where they were kept, fires that paradoxically preserved them by turning them into terracotta. When we read them now, we see tables of numbers, rows and columns tracking the path of Venus or Jupiter across the background stars. The Babylonians discovered that the movements of the planets, while complicated, are not random. They follow cycles. If you watch long enough and record carefully enough, you can begin to predict where a planet will be on a future night. They got very good at this. They could predict the rising and setting of planets with impressive accuracy. And, most importantly, they learned to predict eclipses, though in a rough and general way, by noticing the cycles in which eclipses repeat. An eclipse, the darkening of the sun or the moon, could be a frightening thing, an omen. To predict it was to gain a measure of calm control over the world. Alongside their careful number-keeping, the Babylonians gave us a framework that still quietly shapes our lives today. They divided the path of the sun, moon, and planets through the sky into 12 equal sections, naming each section after a constellation that lay within it. This is the origin of the zodiac. The word itself comes from a Greek word meaning circle of little animals, but the idea is Babylonian. The zodiac was a map of the sky, a way of organizing the apparent motion of the sun over the course of a year. The sun spends roughly 1 month in each sign. This system, modified over time by the Greeks and others, is still with us, in newspaper horoscopes and casual conversation, though its original purpose was strictly astronomical, a tool for tracking the calendar and the planets. And there is another Babylonian legacy, an even quieter one, woven so deeply into the fabric of our daily lives that we hardly notice it. The Babylonians counted in a base 60 system, meaning they built their numbers around the number 60 rather than the number 10 that we use for most things. This base 60 system is the reason we divide an hour into 60 minutes and a minute into 60 seconds. It is the reason we divide a circle into 360 degrees. Every time you glance at a clock and see the minute hand click forward, you are inheriting a choice made by Babylonian mathematicians and astronomers thousands of years ago. They found the number 60 very useful because it can be divided evenly by many smaller numbers: 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30 all fit cleanly into 60. This made calculations, especially calculations with fractions, much smoother in a world without our modern decimal system. The numbers on the clay tablets, the positions of the stars, were recorded in this base 60 system. It is a soft, persistent echo from the ancient past, a reminder that the way we measure time and space is not inevitable. It is a choice, a gift, handed down across more than 3,000 years. Let your mind drift for a moment to another ancient river, the Nile. In Egypt, the sky was watched just as carefully, but for a reason tied directly to the land itself. The Nile River flooded every year, rising in the late summer and spilling out over the fields, depositing a rich, dark silt that made the land fertile and productive. The flood was the heartbeat of Egyptian agriculture. Knowing when it was coming was essential. The Egyptian priests and astronomers noticed a connection. The star Sirius, the brightest star in the entire night sky, reappears in the morning sky each year after a period of being hidden behind the glare of the sun. Its first rising, just before dawn, after months of absence, is called the heliacal rising, and in ancient Egypt, this heliacal rising of Sirius happened at roughly the same time as the beginning of the Nile flood. The star and the river were linked. Watching the sky meant knowing when the water would rise. The sky was not just a distant realm of gods and patterns. It was a practical, life-giving calendar, a signal for when to plant and when to harvest. The precision of the Egyptian year, based on this and other observations, was remarkable. A year of 365 days, divided into 3 seasons of 4 months each, a system that eventually influenced the calendar we use today. The ancient sky watchers, whether in Mesopotamia or Egypt, or on the windy plains of what is now England, were doing something profoundly human. They were taking the vast, overwhelming, silent face of the night sky and breaking it down into manageable pieces. Stones that catch the sunrise, tablets that track the planets, stars that predict the flood. They were building the first foundations of a science, not with equations and formulas, but with stone and clay and careful, repeated looking. They were the ones who first asked, with enough patience to last generations, what are those lights, and how do they move, and what is our place among them? Their answers were incomplete, and many of their reasons are now lost to us. But their questions are our questions, and their patient watching, in the deep dark of a world lit only by fire and starlight, is the bedrock on which everything that follows in this long, slow story rests. They gave us the first records, the first tools, the first gentle proof that the universe is not chaos, It has rhythms, it has patterns, and with enough time and enough care, those patterns can be known. So the stones stand on the plain, the clay tablets sit in museums, the star Sirius still rises, every year, just before the sun. The zodiac still wheels overhead, and the base 60 count still ticks in every clock. These are the first gifts of the first astronomers, and from here, from this quiet foundation, the story will slowly move, over centuries and across seas, toward new questions and new ways of asking them. From that quiet foundation of stone and clay and patient watching, the story moves across the sea, to a world where the watching began to turn into something more structured, something we might recognize now as the first steps toward a formal theory of the sky. The place was ancient Greece, and the time stretched across several centuries before the Common Era. The Greeks did not invent astronomy. They inherited it, in part from the Babylonians and Egyptians, whose records and observations had accumulated over thousands of years. But the Greeks brought something new to the table. They brought a kind of organized questioning. They wanted not just to record the motions of the sky, but to explain them, to fit them into a system, a model, a picture of the whole universe that made sense to the human mind. They were philosophers as much as astronomers, and their questions were deep and calm and persistent. What is the shape of the world? What holds it up? Why do the planets wander while the other stars stay fixed? Where is our place in the great, dark order of things? One of the most influential of these early Greek thinkers was a man named Aristotle, who lived in the 4th century before the Common Era. Aristotle looked at the world around him and at the sky above, and he reasoned his way toward a picture that felt solid and complete. He saw that objects fall toward the ground, straight down, which suggested to him that the earth is the natural center of all motion. The heavy things, the earth and water, settle at the center. The lighter things, the air and fire, rise upward. And the celestial bodies, the sun, the moon, the planets, and the stars, they are made of a fifth perfect substance, and they move in perfect circles around the central earth. In Aristotle's model, the earth was a sphere, fixed and unmoving, and everything else was carried around it on a series of transparent, concentric spheres. The moon was on the closest sphere, then Mercury, then Venus, then the sun, then Mars, Jupiter, Saturn, and beyond all of these, the sphere of the fixed stars, which turned once a day and carried all the other spheres with it. It was a beautiful, orderly, nested system. It felt right. It matched the everyday experience of standing on solid, unmoving ground and watching the sun and stars wheel overhead. And it placed humanity, placed the earth, at the very center of creation. This was a deeply comforting thought, and it would hold sway over the human imagination for a very, very long time. But not all Greek thinking was about building grand philosophical pictures. Some of it was about measuring, with surprising precision, the world we actually live on. A few decades after Aristotle, around the year 240 before the Common Era, a Greek scholar named Eratosthenes did something remarkable. He lived in Alexandria, in Egypt, which was then a Greek city. He was the chief librarian of the Great Library of Alexandria, a place we will touch on again later. Eratosthenes heard a story. He heard that in the city of Syene, far to the south of Alexandria, on the longest day of the year, the sun at noon shone straight down to the bottom of a deep well, lighting the water below. This meant the sun was directly overhead. But on that same day, at that same time, in Alexandria, the sun was not directly overhead. A tall pillar cast a short shadow. Eratosthenes measured the angle of that shadow. It was about 1/50th of a full circle. He reasoned that if the earth is a sphere, the difference in the angle of the sun's rays at the two locations was due to the curve of the earth's surface between them. He knew the distance between Alexandria and Syene, roughly 5,000 stadia, a Greek unit of distance. By multiplying that distance by 50, he calculated the full circumference of the earth. His number was remarkably close to the true value, within a few percent. The exact length of a stadion is still debated by historians, so we cannot say with perfect precision what his number would be in modern miles. But the method was sound, and the result was astonishingly good for an experiment conducted more than 2,000 years ago, with nothing but a stick, a well, and a careful, thinking mind. Think about that for a moment. No satellites, no photographs, no telescopes, just a man, a shadow, and a question. Eratosthenes measured the curve of the Earth from a single point on its surface. He did not need to travel around the whole world. He used the sun as a giant, natural measuring tool, and he let his mind travel where his feet could not. This is the quiet power of early Greek astronomy at its best. Not just grand ideas, but careful, grounded measurements that confirmed, in their own slow way, that the Earth is a sphere spinning in a vast, dark space. The knowledge was there, earned and solid. It would be passed down, and sometimes it would be forgotten for a time in some places, but it would never fully disappear. The patient work of cataloguing the sky continued too. A century after Eratosthenes, in the 2nd century before the Common Era, a Greek astronomer named Hipparchus set out to make a precise map of the stars. He worked on the island of Rhodes in the eastern Mediterranean, and he compiled a catalogue of about 1,000 stars, recording their positions and their brightness. This was the first systematic star catalogue in the Greek tradition, a careful list that would be used for centuries. But Hipparchus did something else, something that revealed a very slow, very subtle truth about our planet. He compared his own measurements of the stars' positions with much older records from Babylonian astronomers, and he noticed a small, persistent shift. The positions of the stars relative to the equinox points, the places where the sun crosses the celestial equator, had changed. The whole framework of the sky had shifted by a tiny amount. Hipparchus realized that the Earth's axis itself is slowly wobbling, like the slow, steady wobble of a spinning top as it begins to lose speed. This wobble causes the equinox points to drift westward along the zodiac, very slowly, over a cycle that takes about 26,000 years to complete. The name for this gentle, almost imperceptible motion is precession. It is the slowest moving clock in the sky. In a single human lifetime, the change is almost too small to notice. But across centuries, it becomes measurable. The North Star we use today, Polaris, was not the North Star in Hipparchus's time. The axis pointed to a different part of the sky, and in many thousands of years from now, a different star, Vega, will take its place as the pole star. The sky is not a fixed, eternal thing. It breathes, it shifts, it turns on cycles so long that only the most patient record-keeping can detect them. Hipparchus, looking at old Babylonian tablets and comparing them to his own careful notes, found one of those cycles. He found the slow breath of the Earth. All of this earlier Greek work was gathered together, centuries later, by a man whose name would become synonymous with astronomy for more than a millennium. His name was Claudius Ptolemy, and he lived in Alexandria, in Egypt, in the 2nd century of the Common Era, around the year 150. Ptolemy was a compiler and a synthesizer. He took the observations of Hipparchus, the philosophical framework of Aristotle, and the mathematical tools of his own time, and he wove them into a single, comprehensive book. The book's original Greek title was something like Mathematical Treatise, but it became known to history by its Arabic name, the Almagest, which simply means the greatest. And in its time, and for a very long time afterward, it was. The Almagest laid out a complete system of astronomy. It explained how to predict the motions of the sun, the moon, and the 5 visible planets, using a system of circles within circles, small epicycles riding on larger deferents, all centered on an unmoving Earth. The mathematics was detailed and it worked, mostly. It could predict planetary positions with reasonable accuracy for many years, though the model was complex and required constant small adjustments. Ptolemy's Earth-centered model, what we now call the geocentric model, was not a wild guess. It was a careful, rational attempt to save the appearances, as the Greeks said. to make a mathematical model that matched what the eye actually sees. And what the eye sees is the sun and moon and stars rising and setting around a fixed point. The idea that the earth moves under our feet is not something we feel. It is a leap of imagination, a trust in measurements over sensation. Ptolemy's model respected sensation. It kept the earth still and at the center, and it wrapped the universe in perfect, though complicated circles. Because it worked so well as a predictive tool, and because it fit so naturally with the philosophical and religious sense that humanity is the center of creation, Ptolemy's Almagest became the standard textbook of astronomy. It was copied, studied, and commented upon for generation after generation. The model it described persisted, largely unchallenged in any fundamental way, for more than 1,000 years. That is a thought to sit with for a moment. For over 1,000 years, the core picture of the universe, the Earth sitting still at the center with everything circling around it on crystal spheres, was simply the way things were. It was not a theory, it was reality. The Almagest was not just a book, it was the sky, explained. The Greeks gave us this, a universe that was ordered, measurable, and, in its own complex way, predictable. They asked not just what the sky does, but why. And their answer, the Earth-centered cosmos, was a beautiful and durable one. It would take a very long time, and a great deal of quiet, careful work by many different people in many different lands, before that picture would begin to shift, before the center would give way. But the foundations they built, the mathematics, the geometry, the very idea that the sky could be understood through reason and measurement, those foundations would last. They would be preserved and extended by other cultures, in other parts of the world, during the long centuries when Greek civilization itself faded and changed. The story does not stop here, it widens. The story does not stop here, it widens. While Aristotle and Ptolemy were shaping the Greek tradition, and while that tradition was slowly spreading around the Mediterranean, other eyes were looking up in other parts of the world. Eyes that belonged to entirely different cultures, with their own languages, their own philosophies, their own careful systems of record-keeping. These traditions developed largely on their own, with little or no contact with Greek astronomy. They were separate streams of human curiosity, flowing independently toward the same great ocean of questions. And what is remarkable, in a quiet and gentle way, is that some of these streams arrived at similar ideas, similar insights, without ever knowing about each other. The human mind, when it looks at the same sky, tends to ask the same kinds of questions, and sometimes it finds the same kinds of answers. In China, the watching of the sky was an imperial duty. The emperor was considered the son of heaven, and the sky was seen as a kind of mirror of the earthly realm. What happened in the heavens reflected, and sometimes foretold, what would happen on earth. So keeping an accurate, unbroken record of the sky was a matter of state importance. For centuries, Chinese astronomers maintained detailed court diaries of what they saw. They recorded eclipses with great precision. They noted the appearance of new stars, what we would now call novae or supernovae. They tracked comets as they moved slowly across the constellations, describing their tails and their changing brightness. The records were kept on silk and on paper, in carefully preserved scrolls and books, passed down through the dynasties. The continuity of this record-keeping is one of the great achievements in the history of astronomy. Some of the Chinese star records go back more than 4,000 years, though the most detailed and reliable continuous records date from around 2,500 years ago. One of the most famous entries in these Chinese records concerns an event that happened in the year 1054 of the Common Era. On the 4th of July of that year, according to the records, a bright new star appeared in the sky. It was visible even during the day for a period of several weeks, and it remained visible at night for nearly 2 years before fading from sight. The Chinese astronomers noted its position carefully, in the constellation we now call Taurus, the Bull. What they had witnessed, without knowing it, was a supernova, the explosive death of a massive star. The remains of that explosion are still visible today through telescopes. We call it the Crab Nebula, a beautiful, cloudy patch of expanding gas and dust, exactly in the spot where the Chinese records placed the guest star, as they called it. The connection between the historical record and the physical object is direct and unbroken. A modern astronomer can point a telescope at the Crab Nebula and know, with calm certainty, that the light from its formation reached Earth and was seen and recorded by patient watchers in China almost 1,000 years ago. The record is a thread that ties the ancient world to the present, a single, continuous line of observation. Chinese astronomy also developed its own detailed star maps and its own systems of celestial coordinates, different from the Greek system. They divided the sky into many small groups of stars, not quite the same as the Greek constellations, and they tracked the movements of the planets through these groups. They built instruments, large bronze armillary spheres, which were models of the sky made of nested rings, allowing an astronomer to measure the positions of celestial bodies with considerable accuracy. All of this was done, for the most part, without any knowledge of what the Greeks were doing. The two traditions were worlds apart. The Chinese astronomers worked within their own framework of understanding, answering their own questions, serving their own empire. Their legacy is a vast, quiet archive of the sky's behavior over millennia, an archive that modern astronomers still consult when they want to know how a particular star or a particular comet has behaved over very long periods of time. Across the Pacific Ocean, another civilization was watching the sky with extraordinary precision. The Mayan people of Central America, in what is now southern Mexico and Guatemala, built great stone cities and developed a sophisticated written language and a deep, complex understanding of time. For the Maya, time was not just a simple flow from past to future. It was a woven fabric of repeating cycles, multiple calendars running simultaneously, meshing together like gears in a great cosmic machine. The most important of these calendars was the 260-day sacred calendar, but they also tracked a solar year of 365 days with an accuracy that rivals our modern Gregorian calendar. The Mayan astronomers knew the length of the solar year to a precision that was not matched in Europe until many centuries later. But perhaps the most impressive focus of Mayan astronomy was the planet Venus. Venus is the brightest planet in the sky, the morning star and the evening star. The Maya watched its risings and settings with an almost reverential care. They compiled tables that predicted the movements of Venus with remarkable accuracy, understanding its cycle of visibility and invisibility. They knew that Venus appears as the morning star for about 236 days, then disappears for about 90 days, then reappears as the evening star for another 250 days or so, then vanishes again before the cycle begins anew. They recorded all this in their codices, their folded books made of fig bark paper. The most famous surviving example is the Dresden Codex, which contains detailed Venus tables, page after page of precise numbers and dates, all worked out without telescopes, without any magnification at all, just the patient, repeated observation of the planet's position on the horizon at dawn and dusk. The Mayan buildings themselves were often aligned with astronomical events. Temples and pyramids were positioned so that on certain key days of the year, the solstices or the equinoxes, the sun would rise or set in a particular notch of a staircase or through a specific doorway. The sky was built into the stone of their cities. The calendar was not just an abstract idea, it was a physical presence, a rhythm you could walk through. Unfortunately, much of the written Mayan record was destroyed during the Spanish conquest in the 16th century. Only a few of their codices survive. The knowledge that was lost cannot be fully recovered. We are left with fragments, beautiful and tantalizing, that hint at a vast and intricate system of thought about the sky and about time. The fragments themselves are a reminder that the historical record is never complete. There are whole libraries of human thought that have vanished, and we can only sit with the quiet awareness of that loss, knowing that what we do have is only a part of a much larger whole. Then, turning west across another ocean to the Indian subcontinent, we find another independent tradition. Indian astronomy is ancient, with roots in the Vedas, the oldest sacred texts of Hinduism, which contain hymns and passages about the sun, the moon, and the stars, dating back more than 3,000 years. But the most notable figure in early classical Indian astronomy is a man named Aryabhata, who lived in the late 5th century of the Common Era. In the year 499, when he was just 23 years old, Aryabhata wrote a compact but profound book called the Aryabhatiya. In it, he proposed a series of ideas that were, in their time, quietly revolutionary. The most striking of Aryabhata's ideas was his explanation for the daily rising and setting of the stars. The standard view, the view held in the Greek tradition and in most other places, was that the earth sits still and the entire sky rotates around it once a day. Aryabhata suggested something different. He suggested that the earth itself rotates on its axis, spinning from west to east. This spinning, he argued, creates the illusion that the sky is moving. The stars are not rushing around us at unimaginable speeds. We are the ones turning, slowly and smoothly, and the motion we see is a reflection of our own motion. This is a profound shift in perspective. It is the same insight that would later be championed by Copernicus, though Aryabhata did not go so far as to place the sun at the center of the solar system. His model was still Earth-centered, but with a spinning Earth. It was a half-step, but an important one. Aryabhata also worked on the mathematics of planetary motion, calculating the length of the year with impressive precision, and he correctly explained the phases of the moon and the causes of eclipses. He understood that the moon shines by reflected sunlight, and that an eclipse is simply the shadow of the earth falling on the moon, or the shadow of the moon falling on the earth. This was not superstition. It was calm, rational, mathematical astronomy. The work of Aryabhata was carried forward by later Indian astronomers, who refined his calculations and developed their own instruments and techniques. This tradition, like the Chinese and the Mayan, developed largely in isolation from the Greek world, though there were some points of contact, some slow exchanges of ideas along the trade routes. But the core of the work was indigenous, arising from its own cultural and intellectual soil. It is worth pausing here, in the quiet of this widening story, to acknowledge the incompleteness of the record. Wars, conquests, the decay of materials, the simple erosion of centuries, all of these have erased things that once were known. The burning of Mayan codices by Spanish missionaries, the destruction of Chinese court archives during dynastic upheavals, the fragile nature of palm leaf manuscripts in the Indian climate. We know the names of a few great astronomers from these traditions, but there must have been many more whose names and works are gone. The history of astronomy is not a complete library. It is a shelf with many gaps, many missing volumes, and those gaps are not something to fill with guesswork. They are simply there, quiet spaces in the story where the voices have faded. The not knowing is part of the calm. We can acknowledge that people were watching the sky, carefully and intelligently, in many places over many centuries, and that the full richness of their watching is now beyond our reach. That is not a problem to solve. It is just a fact to sit with, a soft, open space at the edge of our understanding. And so the story widens, across the Pacific and the Indian Ocean, across the mountains and the jungles, across the centuries. The same sky, the same patient questions, arising in human minds, separated by immense distances and by the slow, heavy weight of time. The Earth-centered universe of the Greeks was not the only way to think about the cosmos. The Chinese had their imperial records, the Maya had their interlocking calendars, the Indians had their spinning earth. These were all different ways of holding the sky in the mind, different languages for describing the same ancient light. The stage is now set for a period of preservation and synthesis, a time when these separate streams of knowledge would begin to flow together, slowly and carefully, in the great houses of learning of a new and vibrant civilization. The story continues, not in a straight line, but in a gentle, gathering curve. The story continues, not in a straight line, but in a gentle, gathering curve. and that curve now bends toward a city that rose to prominence in the 8th century of the Common Era, a city built on the banks of the Tigris River in what is now Iraq. The city was Baghdad, and within Baghdad there was a place known as the House of Wisdom. It was not a single building, exactly, though the name suggests a library or a school. It was more of a scholarly institution, a gathering place for scholars and translators and thinkers, supported by the ruling caliphs of the time, who valued knowledge and saw learning as a noble pursuit. The House of Wisdom became the center of a vast and careful project, the translation of the great works of Greek philosophy and science into Arabic. This was the beginning of what we now call the Islamic Golden Age, a period lasting several centuries during which the Islamic world became the primary steward of ancient knowledge and the primary engine of new discovery in astronomy, mathematics, medicine, and many other fields. The work began with translation. Scholars in Baghdad, many of them Christians and Jews and Muslims working side by side, systematically gathered Greek manuscripts from the old Byzantine libraries and translated them into Arabic. They translated Ptolemy's Almagest. They translated the works of Aristotle and Hipparchus and Euclid. They also absorbed knowledge from Persia and India, bringing together the separate streams of Greek, Indian, and Persian astronomy into a single, flowing river. This was not a passive act of copying. The translators were often scholars in their own right, and they wrote commentaries and corrections and improvements as they worked. They preserved what was valuable, but they also questioned it. They checked Ptolemy's numbers against their own observations. They refined the star catalogues. They kept the flame of Greek astronomy alive during centuries when, in Europe, much of that knowledge had faded from active use. The Islamic world, stretching from Spain across North Africa and the Middle East to Central Asia, became the keeper of the sky. One of the most notable of these early Islamic astronomers was a man named al-Battani, who lived in the late 9th and early 10th centuries. He was born in what is now Turkey, and he spent much of his life in the city of Raqqa, on the Euphrates River, where he built his own observatory. Al-Battani was a meticulous observer. He spent decades measuring the positions of the sun, the moon, and the planets with a level of precision that improved on Ptolemy. He recalculated the length of the solar year, the time it takes for the Earth, though he would not have thought of it that way, to complete one full orbit around the sun. His value for the year was off by only a few minutes from the modern measurement. He also measured the angle of the tilt of the Earth's axis, what is called the obliquity of the ecliptic, and found it to be about 23 degrees and 35 minutes. This was a very good measurement for his time. Al-Battani's star catalogue, which updated and corrected Hipparchus and Ptolemy, was used by astronomers in both the Islamic world and later in Europe for many centuries. His work was a bridge, a careful, steady arc of numbers and observations that connected the ancient world to the medieval and, eventually, to the modern. The astronomers of this period did not just observe, they also built. They designed and refined a beautiful instrument called the astrolabe. An astrolabe is, in its simplest form, a flat, circular plate of brass or another metal, engraved with intricate scales and fitted with a rotating overlay that represents the night sky. By adjusting the moving parts to match the date and the position of a particular star, a user could solve a wide range of astronomical and timekeeping problems. You could use an astrolabe to find the time of night, to determine when the sun would rise and set, to measure the height of a star above the horizon, to find your direction of travel, and even to cast a basic horoscope. It was a portable sky, a calculating device that you could hold in one hand. The astrolabe had its origins in Greek and possibly Indian design, but it was the Islamic instrument makers who brought it to its highest level of artistry and precision. The engravings were often exquisite, with flowing Arabic calligraphy and delicate geometric patterns. An astrolabe was both a scientific tool and a work of art, an object of quiet beauty made for the contemplation of the stars. It was used by travelers in the desert, by sailors at sea, and by astronomers in their observatories. The astrolabe is a symbol of this entire period, knowledge made portable, preserved in metal, carried from city to city, from generation to generation. And the observing continued, night after patient night. A Persian astronomer named Abd al-Rahman al-Sufi, who lived in the 10th century, published a book called the Book of Fixed Stars. It was an update of Ptolemy's star catalogue, but al-Sufi added his own observations and corrections. He recorded the brightness of the stars, their colors, their positions. He included beautiful constellation drawings, showing the stars as they appeared to the eye and as they appeared in the Ptolemaic tradition. But in the course of his careful recording, al-Sufi noted something that had not been clearly recorded before. He described a small, faint cloud in the sky, located in the constellation of Andromeda. He called it a little cloud. This was an observation with the unaided eye, no telescope involved. Al-Sufi was describing what we now know as the Andromeda Galaxy, the nearest large spiral galaxy to our own Milky Way. It is a vast city of stars, containing perhaps 1 trillion suns, so far away that its light takes more than 2 million years to reach us. And to al-Sufi, it was a gentle smudge, a small patch of haze, noted calmly in a book among the other fixed stars. He did not know what it was. No one would know for almost another 1,000 years. But he saw it, and he wrote it down. The Andromeda Galaxy was in the Book of Fixed Stars, waiting quietly for its true nature to be understood. The Islamic Golden Age of astronomy was not a single burst of activity. It was a sustained effort, lasting from roughly the 8th century to the 14th century and beyond, with many different scholars working in many different cities. In Cairo, the astronomer Ibn Yunus compiled a set of astronomical tables that were used for centuries. In Persia, the mathematician and poet Omar Khayyam, known in the West for his poetry, led a team of astronomers who calculated a solar calendar that was even more accurate than the Gregorian calendar we use today. In Maraga, in what is now northwestern Iran, the astronomer Nasir al-Din al-Tusi built a large observatory in the 13th century, where he and his colleagues made careful observations of the planets and began to develop new mathematical models that subtly challenged the Ptolemaic system. They worked on ways to explain planetary motion without some of the more complicated devices Ptolemy had used. This work, quiet and technical, would later find echoes in Europe, in the work of Copernicus. The chain of influence is gentle and long, stretching across languages and continents. Ideas travel slowly, carried in manuscripts, translated, commented upon, refined. The astronomy of the Islamic Golden Age was the vital middle link in that chain, holding the past and nurturing the future. Think for a moment about what this means. During the centuries when Europe was largely in a period of slow development in the sciences, when Greek and Roman learning had become fragmented and scattered, it was the scholars of the Islamic world who kept the sky alive. They did not just preserve it like a pressed flower in a book. They tended it like a garden. They added new plants. They cross-pollinated different traditions. They improved the tools. They made the measurements more precise. The names of the stars themselves bear witness to this. Many of the common star names we use today, the names that roll softly off the tongue, are Arabic in origin. Aldebaran, the bright eye of Taurus the bull; Betelgeuse, the red shoulder of Orion; Rigel, the blue foot of Orion; Deneb, the tail of the swan; Fomalhaut, the mouth of the fish. These are not Greek names, not Latin names, not modern names. They are Arabic words, transmitted through the centuries, now spoken by astronomers around the world. Every time one of these star names is spoken, it is a quiet tribute to the scholars of the Islamic Golden Age, a soft reminder that the story of astronomy is a global story, woven from many languages and many cultures. So as you lie here in the dark, letting your mind drift among the stars, think of the astrolabe, a small brass instrument, cooling in the night air on an open rooftop in Baghdad or Damascus or Cordoba. Think of a scholar whose name may now be forgotten, sitting cross-legged with a stylus and a sheet of paper, recording the precise moment a particular star crossed the meridian. Think of the House of Wisdom, not as a grand palace of marble, but as a quiet place of conversation and study, where people of different faiths work together on a shared project of understanding. Think of Al-Sufi's little cloud in Andromeda, a faint patch of light that contains 1,000,000,000,000 suns, noted without fanfare in a book of stars. The sky did not go unwatched during those centuries. It was watched with care and with love, and with rigorous intelligence. The tradition was preserved and deepened. And when the story eventually returned to Europe, when the next slow shift in our understanding of the cosmos began to take shape, it would do so on the shoulders of these patient, careful observers, whose names we should not forget, and whose work still whispers to us, softly, in the dark. And when the story eventually returned to Europe, when the next slow shift in our understanding of the cosmos began to take shape, it did so not with a bang, not with a dramatic announcement, but with a quiet book and a quiet man. The man was Nicolaus Copernicus. He was born in the year 1473 in the city of Torun, in what is now Poland. He studied at various universities in Krakow and in Italy, learning mathematics, medicine, law, and of course, astronomy. He became a canon of the Catholic Church, a kind of administrative and religious official, and he spent much of his adult life in the northern Polish town of Frauenburg, now called Frombork, where he lived in a modest tower by the cathedral wall. From that tower he looked at the sky. He read the old books, the Almagest of Ptolemy, the works of the Islamic astronomers, the latest tables of planetary positions. And slowly, carefully, over decades, he came to believe that the old model of the cosmos needed a quiet but fundamental revision. The old model, the Ptolemaic model, placed the Earth at the center. It was the model that had been taught and believed for more than 1,000 years. It was the model that matched everyday experience. But Copernicus, looking at the mathematical details, found the Ptolemaic system to be increasingly cumbersome. To make the model match the actual observed motions of the planets, astronomers over the centuries had added more and more small circles, called epicycles, wheels within wheels, adjustments upon adjustments. The elegance of the original Greek vision had become tangled. Copernicus wondered if there might be a simpler, more graceful way to arrange the pieces. He went back to some of the old ideas that had been whispered in the ancient world. A few Greek thinkers, like Aristarchus of Samos, had suggested that the sun might be at the center, but their ideas had never taken hold. Copernicus picked up that thread. He asked a quiet question. What if the sun, not the Earth, sits at the center of the solar system? What if the Earth is just another planet, circling the sun like the others? This is the idea now called heliocentric, which simply means sun-centered. The word comes from the Greek word helios, meaning sun. In Copernicus's new arrangement, the sun stood still at the center. Mercury, then Venus, then the Earth, then Mars, Jupiter, and Saturn all orbited around it in concentric circles. The moon, alone, orbited the Earth. The daily rising and setting of the sun and stars was explained not by the entire universe spinning around a fixed Earth, but by the Earth itself rotating on its axis once each day. The apparent backward motion of the planets, the retrograde loops that had puzzled astronomers for so long, could now be explained as a simple effect of perspective. When the Earth, moving faster on its inner orbit, passed a slower outer planet like Mars, the planet appeared to drift backward against the fixed stars for a time, just as a slower car appears to move backward when you pass it on a highway. Copernicus's model explained this without the need for large epicycles on the planets themselves. It was, in many ways, a cleaner and more elegant system. But Copernicus was cautious. He knew that his idea would be controversial. The Earth-centered model was not just a scientific theory. It was woven into the fabric of philosophy and religion. To move the Earth from the center was to demote humanity from its special place in creation. Copernicus was a churchman himself, and he had no desire to provoke a conflict. So he worked on his theory in private for many years. He circulated a short, unsigned manuscript to a few trusted friends, outlining the basic idea. He continued to gather observations and refine his calculations. He wrote and rewrote his full book, a work he titled De Revolutionibus Orbium Coelestium, which means On the Revolutions of the Heavenly Spheres. And he delayed its publication. Year after year, the manuscript sat in his study, in that quiet tower by the cathedral, while the stars wheeled overhead and the world outside went on with its business. This was not the behavior of a radical revolutionary. This was the behavior of a careful, methodical, perhaps even hesitant man, who wanted his work to be accurate and who understood the weight of what he was proposing. Finally, in the early 1540s, Copernicus was persuaded to publish. A young mathematician named Georg Joachim Rheticus visited Copernicus, learned about the theory, and became a passionate advocate. He helped prepare the manuscript for printing in Nuremberg. The book was published in the year 1543. According to a gentle and long-repeated story, Copernicus, by then an old man of 70, received a printed copy of his book on the very last day of his life. He had suffered a stroke and was in a coma, the story goes. He woke long enough to see the book, touched it, and then died peacefully. The story may be a little too perfect, a little too tidy. The truth is that we cannot be sure of the exact circumstances of his death. But the story endures because it captures a certain truth. The book was the sum of his life, and its arrival marked the end of his long and patient labor. He died in the same year his great work came into the world. And what of the book itself? It was not a bold, sweeping declaration. It was a dense, technical, mathematical work dedicated to the Pope. It began with a preface, inserted by the printer without Copernicus's knowledge, that presented the heliocentric model as merely a mathematical convenience, a tool for calculation, rather than a true description of the physical universe. Copernicus may or may not have believed in the physical truth of his own model. We cannot know his private thoughts with certainty, but his book, carefully read, makes it clear that he did believe it, at least as a powerful and elegant description of the real cosmos. The ideas inside were quiet but profound. They rearranged the furniture of the universe. They put the sun at the center. However, Copernicus's model, for all its elegance, was not perfect. He held on to one of the most deeply held beliefs of ancient astronomy, the belief that the planets must move in perfect circles. A circle was the ideal shape, the perfect form, the only motion worthy of celestial bodies. So Copernicus, even as he moved the sun to the center, kept the orbits circular, and because the orbits of the planets are not, in fact, perfect circles, his model still needed small epicycles to match the observed positions. It was, in the end, only a little more accurate than the Ptolemaic system it sought to replace. The true shape of planetary orbits would not be understood until the work of Johannes Kepler, which we will come to later. For now, it is enough to know that Copernicus made a quiet, incomplete correction. He took the first, crucial step. He shifted the perspective. He suggested, calmly and carefully, that we are not the fixed center of everything. We are passengers on a moving planet, looking out at a universe that is far larger and far stranger than we had imagined. The book, De Revolutionibus, did not cause an immediate uproar. It circulated quietly among astronomers and mathematicians. Some found it interesting, some found it unconvincing. The Catholic Church, for the time being, did not condemn it. The idea spread slowly, over decades, without any wide public acceptance. Most people, including most educated people, continued to believe in the Earth-centered model. It simply felt right. The ground does not move. The wind does not sweep us off our feet as the Earth spins. The whole idea seemed, to many, absurd. And so the heliocentric model waited. It was a seed planted in the soil of European thought, and it would take time to germinate. The quiet reversal had begun, but it was just that, quiet. A slow, patient shift in perspective, one that would take more than a century to fully take hold. This is the nature of the story we are tracing. It is not a story of sudden breakthroughs and dramatic confrontations. It is a story of slow corrections, small adjustments, ideas held for decades before being spoken aloud. Copernicus did not overthrow the old universe. He simply proposed an alternative. He offered a new way of looking at the same data, a new arrangement of the same planets and stars, and he did it with caution, with care, and with a deep sense of the weight of what he was suggesting. His book sat on shelves, in libraries, in the studies of other patient scholars. Some of them nodded along. Some of them shook their heads, but the idea was out. The seed was in the ground. The sun had been placed at the center, and the earth had been set in motion, even if that motion was still imagined as a perfect, unvarying circle. The next steps would require new eyes, new tools, and a new kind of evidence. They would require someone to look at the sky, not just with the naked eye, but with an instrument that could magnify and reveal things that had never been seen before. That instrument was coming. The telescope was about to be turned toward the night sky, and when it was, the quiet reversal that began in a Polish tower would find its most powerful and persuasive voice. That instrument was coming. The telescope was about to be turned toward the night sky, and when it was, the quiet reversal that began in a Polish tower would find its most powerful and persuasive voice. That voice belonged to a man named Galileo Galilei. He was born in the year 1564, in the city of Pisa, in Italy. His father was a musician and a music theorist, a man who studied the mathematics of sound and vibration. From his father, Galileo inherited a deep respect for careful measurement and for the idea that the world could be understood through mathematics. Galileo studied at the university, and he became a professor of mathematics, first at Pisa and then at Padua, in the Republic of Venice. He was a restless, curious mind, interested in many things. He studied motion, the way objects fall and swing. He studied the strength of materials. And, in the year 1609, he heard about a new invention that had appeared in the Netherlands. The invention was called a spyglass. It was a simple tube with a lens at each end, one convex and one concave, that made distant objects appear closer. It was a novelty, a curiosity, used mostly for spotting ships at sea or watching parades from a distance. Galileo heard about this device, and without even seeing one, he figured out the optical principles behind it. He went to his workshop, and he ground his own lenses. He fitted them into a tube of wood and leather, and he made a spyglass that was better than the ones being made in the Netherlands. His first telescope, as we now call it, magnified objects about 3 times. But Galileo was not satisfied. He kept working, kept grinding and polishing lenses, and within a few months he had built an instrument that magnified about 20 times. And then he did something that seems obvious to us now, but which was a quiet stroke of genius at the time. He turned his telescope away from the ships and the parades and the distant hills. He turned it toward the sky. What he saw, night after night, changed everything. Not because it proved Copernicus right all at once, but because it showed, with direct, visible evidence, that the old picture of the universe was incomplete. The sky was not the perfect, unchanging realm that Aristotle and Ptolemy had described. It was a place of roughness and imperfection, and surprising new detail. Galileo was the first person in history to see these things with his own eyes, and he recorded his observations with careful, patient attention, writing down what he saw in notebooks, making sketches, building the case night by night by night. The first thing he looked at was the moon. To the naked eye, the moon is a smooth, round disk, marked with faint, dark patches that people called the Maria, the seas. But through the telescope, even a modest one magnifying 20 times, the moon looked completely different. Galileo saw mountains and valleys. He saw craters, circular depressions with raised rims and central peaks. He saw shadows cast by the mountains at sunrise and sunset on the lunar surface. By measuring the length of these shadows, he was even able to estimate the height of the lunar mountains, using simple geometry. The moon was not a perfect, smooth celestial sphere. It was a world, a place with its own landscape, its own topography. It was, in some fundamental way, like the Earth. This was the first crack in the old distinction between the earthly and the heavenly realms. If the moon had mountains and valleys, if it was rough and imperfect like the Earth, then the old idea that celestial bodies were made of a different, perfect substance began to crumble. Next, Galileo turned his telescope to the planets. When he looked at Jupiter, he saw something that made his heart beat faster, something that he could not quite believe at first. Near the bright disk of Jupiter, he saw 3 small, faint stars, arranged in a straight line. On the next night, he looked again. The 3 small stars had moved, but they had not moved away from Jupiter. They had changed their positions relative to each other, but they were still clustered close to the planet. On the 3rd night, he saw 4 of them, and as he watched over the following weeks, he realized what he was seeing. These were not background stars. They were small bodies, moons, orbiting around Jupiter itself. He watched them swing from one side of the planet to the other, disappear behind it, reappear on the other side. He timed their orbits. He drew their changing positions. And he named them the Medicean stars, after his patrons, the powerful Medici family of Florence, though today we call them the Galilean moons. Their names, given later, are Io, Europa, Ganymede, and Callisto. This discovery was a profound argument against the old Earth-centered model. In the Ptolemaic system, everything orbited the Earth. That was the central claim. But here, directly visible through the telescope, were 4 bodies that clearly, undeniably, orbited Jupiter. Not everything circles the Earth. The Earth is not the sole center of all motion in the universe. There are other centers. There are other moons around other planets. The Copernican idea that the Earth is a planet like the others suddenly seemed much more plausible. If Jupiter can have moons and still move around the Sun, then the Earth can have a moon and still move around the Sun as well. The logic was simple and direct. The telescope had provided a new piece of evidence, a small, quiet, but immensely powerful fact that did not fit into the old picture. Galileo continued his observations. He turned his telescope to the Sun, being careful to project its image onto a piece of paper rather than looking directly at it. And on the face of the Sun he saw spots, dark, irregular blemishes that appeared and faded over time. They moved across the solar disk, showing that the Sun itself rotates. The Sun was not a perfect, unchanging orb of pure light. It had spots. It had imperfections. It rotated. Another piece of the old Aristotelian perfection fell away. He looked at Venus. To the naked eye, Venus is simply a very bright point of light, the morning and evening star. Through the telescope, Galileo saw that Venus goes through phases, just like the moon. It has a thin crescent phase, a half phase, a nearly full phase. In the Ptolemaic system, with Venus orbiting between the Earth and the Sun, there was no way to explain the full range of phases. Venus would always appear as a crescent. But in the Copernican system, with Venus orbiting the Sun and the Earth on a different orbit, the full cycle of phases made perfect sense. It was exactly what you would expect to see. Galileo watched the phases of Venus change over many months, and the evidence was clear. Venus orbits the Sun. Galileo also looked at the Milky Way, that broad, misty band of light that stretches across the night sky. To the naked eye, it is a smooth, soft glow. Through the telescope, Galileo saw that it is made of countless individual stars, so numerous and so faint that their light blends together into a continuous haze. The universe was not only more imperfect than the old model suggested, it was also far, far more vast and more densely populated. All of these discoveries, made over the course of just a few years, Galileo published in a short book called The Starry Messenger, which came out in the year 1610. The book was a sensation. It was written in Latin, the language of scholarship. But Galileo also wrote later works in Italian, the language of ordinary people. He wanted to be read, he wanted to be understood, and he was. The starry messenger made Galileo famous across Europe, but fame brought scrutiny. Galileo's support for the Copernican model, which he now openly advocated, did not sit well with everyone. The Catholic Church, which was a powerful political and intellectual force in Italy, had long endorsed the Aristotelian and Ptolemaic view of the universe. The Bible contains passages that speak of the sun moving and the earth standing still. To challenge that was seen by some as challenging the authority of the Church itself. At first, Galileo faced only quiet warnings. In the year 1616, the Church formally declared the Copernican theory to be foolish and absurd in philosophy, and ordered Galileo not to hold or defend it. Galileo, for a time, complied. He returned to his other studies, the physics of motion, the strength of materials, but the case was not closed. In the year 1623, a new pope was elected, Urban VIII, a man who had been a friend and admirer of Galileo. Galileo thought the time might be right to reopen the question. He wrote a new book called Dialogue Concerning the Two Chief World Systems, which was published in 1632. The book was structured as a conversation between three characters: Salviati, who argued for the Copernican view; Sagredo, an intelligent and open-minded listener; and Simplicio, who argued for the old Aristotelian view. It was a brilliant piece of writing, clear and engaging and persuasive. But it was also a provocation. The Pope, who had urged Galileo to treat the Copernican theory as a hypothesis only, not as proven fact, was not pleased. Worse, Galileo had placed some of the Pope's own arguments into the mouth of Simplicio, the simple-minded defender of the old view. The Church summoned Galileo to Rome. In 1633, at the age of 69, he was brought before the Inquisition. Under threat of torture, he was forced to publicly renounce the Copernican theory. The story, perhaps apocryphal, says that after his recantation, he muttered under his breath, "And yet it moves." We do not know if he actually said this. It may be a later invention. But the story captures the quiet, stubborn truth of his situation. The earth moves, whether the authorities accept it or not. Galileo was sentenced to house arrest for the remainder of his life. He lived for another 9 years in his villa in Arcetri, near Florence, where he was allowed to receive visitors and to work. He turned his attention back to the physics of motion, writing his final and greatest scientific book, The Two New Sciences. He went blind in his later years, a quiet irony for a man who had seen so much that no human had ever seen before. He died in 1642, still under house arrest, still watched, still quieted. But his work could not be undone. The telescope was loose in the world. Other astronomers in other countries were building their own instruments, pointing them at the sky, seeing the craters on the moon, and the moons of Jupiter and the phases of Venus. The old model, no matter how fiercely defended, could no longer explain what anyone with a good telescope could see with their own eyes. The evidence was physical, it was visible, it was repeatable. Galileo's patient, night-by-night observations had provided that evidence. He had not proved the Copernican model in every detail. That would require more work, but he had shown, clearly and irrevocably, that the old Earth-centered universe was not the full story. The sky was a physical place, governed by the same laws as the Earth, and we were not its fixed and special center. The quiet reversal that Copernicus had begun, Galileo had brought into the light. And the next step, the step that would perfect the model and explain the motions of the planets with true precision, was already being taken by another patient observer, working with a different kind of tool, not a telescope, but a long, careful, exquisitely precise set of measurements of the planet's positions, gathered over decades by a Danish nobleman and his quiet, brilliant successor. The next step, The step that would perfect the model and explain the motions of the planets with true precision was already being taken by another patient observer. He was working not with a telescope, but with a long, careful, exquisitely precise set of measurements of the planet's positions, gathered over decades by a Danish nobleman and his quiet, brilliant successor. The nobleman was Tycho Brahe. The successor was Johannes Kepler. Together, across the turn of the 17th century, they would give the world the true shape of planetary motion, and in doing so, they would set the stage for an even deeper understanding of why the planets move as they do. Tycho Brahe was born in the year 1546 to a wealthy and powerful Danish family. He was a larger-than-life figure in many ways, a man of grand gestures and strong opinions. But when it came to the sky, he was a model of patience and precision. As a young man, he witnessed a partial solar eclipse and was struck not so much by the eclipse itself, as by the fact that its time of occurrence had been predicted. The idea that the movements of the heavens could be forecast with accuracy captured his imagination. He decided to devote his life to improving the accuracy of astronomical measurements. He studied the existing tables of planetary positions and found them full of errors, sometimes off by several degrees. He wanted to correct them. He wanted to build the best, most precise astronomical data the world had ever known. Tycho's opportunity came in a remarkable way. The King of Denmark, Frederick II, granted him the island of Hven, a small island in the strait between Denmark and Sweden. There, Tycho built a magnificent observatory, which he named Uraniborg, the Castle of the Heavens. It was not a simple tower. It was a sprawling complex with workshops for building instruments, rooms for visiting scholars, and even a paper mill to supply his printing press. Tycho filled Uraniborg with enormous and exquisitely calibrated instruments. He had great brass quadrants for measuring the altitude of stars. He had large sextants for measuring the angles between celestial bodies. He had armillary spheres, elegant frameworks of rings that modeled the movements of the sky. These instruments were built on a scale never seen before. Some of them were large enough that they required several people to operate, and they were all built with a single purpose: to measure the positions of the stars and planets with the greatest possible accuracy. Before the telescope, this was the only way to do astronomy. You measured angles. You noted the exact time a star crossed the meridian, the imaginary line that runs from north to south through the zenith, the point directly overhead. You recorded the position of a planet relative to nearby fixed stars. You did this night after night, year after year, building up a record of celestial positions that was as complete and as error-free as human hands and eyes could make it. Tycho's observations were the most accurate ever made without a telescope. He reduced the error in planetary positions to about 1 or 2 minutes of arc. To understand how small that is, imagine a circle divided into 360 degrees. Each degree is divided into 60 minutes. 1 minute of arc is about the width of a small coin seen from a distance of a football field. Tycho could measure positions that precisely using only his naked eye and his great brass instruments. It was a labor of immense dedication, and it produced a treasure trove of data, decades worth of precise, consistent observations. Tycho did not accept the Copernican model. He had his own system, a kind of compromise in which the planets orbited the sun, but the sun itself orbited the central, fixed Earth. It was an elegant attempt to keep the mathematical advantages of Copernicus while retaining the philosophical comfort of a stationary Earth. But the true value of Tycho's work was not his theoretical model. It was his data, the numbers themselves, the careful, nightly record of where Mars and Venus and Jupiter were located against the backdrop of the fixed stars. And that data fell, in the final years of Tycho's life, into the hands of the man who would use it to find the true shape of the heavens. That man was Johannes Kepler. Kepler was born in the year 1571 in what is now Germany. He was a quiet, deeply religious man, a mathematician and a mystic, who believed that the universe was built on a beautiful, mathematical harmony. He had written a book called the Mysterium Cosmographicum, the Cosmic Mystery, in which he tried to explain the distances of the planets from the Sun using the 5 perfect Platonic solids, nested one inside the other. The idea was elegant and deeply satisfying to him, but it did not quite match the observations. Kepler knew he needed better data, and the best data in the world belonged to Tycho Brahe. In the year 1600, Kepler traveled to Prague, where Tycho had recently become the imperial mathematician to the Holy Roman Emperor. Tycho was aging, and he needed a skilled mathematician to help him analyze his mountain of observations. The two men had a tense and complicated relationship. They were very different personalities. Tycho was a proud, aristocratic man, protective of his hard-won data. Kepler was a younger, more theoretical mind, hungry to find the deeper patterns. They argued, they parted ways briefly, they reconciled. But in the end, Tycho gave Kepler access to some of his observations, specifically the long and detailed record of the motion of Mars. Mars was the planet whose orbit had given astronomers the most trouble. Its retrograde loops and its varying brightness were the hardest to explain with any simple system of circles. Tycho may have given Kepler the Mars data because it was the most difficult problem, the sternest test of any model. And then, quite unexpectedly, Tycho died. In the year 1601, Kepler was appointed his successor as imperial mathematician. He gained full access to Tycho's data, and he set to work. What followed was years of painstaking, frustrating, brilliant labor. Kepler tried one model after another. He fit circles to the orbit of Mars, then circles within circles. He calculated and recalculated. Each time, the model would almost work, but not quite. There was always a small discrepancy, a stubborn error of about 8 minutes of arc. A lesser scientist might have ignored the error, dismissed it as a flaw in the data. But Kepler knew that Tycho's observations were too good. An 8-minute error was not possible in Tycho's data. The error had to be in the model, so Kepler abandoned the circle. He tried other shapes, and after much trial and error, he found that the orbit of Mars fit beautifully into an ellipse, an oval shape, with the Sun at one of the 2 focal points of the ellipse. This was a quiet revolution. The perfect circles that had governed astronomy since the time of Plato and Aristotle were gone. The planets moved in ellipses, slightly flattened circles, and their speed varied as they moved. They moved faster when they were closer to the Sun, and slower when they were farther away. This was not a small correction. It was a new kind of motion entirely. Kepler published this discovery in the year 1609 in a book called Astronomia Nova, the New Astronomy. It was the first of his 3 laws of planetary motion. The first law states that planets move in ellipses with the Sun at one focus. The second law, published in the same book, states that a line drawn from the Sun to a planet sweeps out equal areas in equal times. This is the law that describes the changing speed of the planet in its orbit. A decade later, in 1619, he published his third law, which relates the time a planet takes to orbit the Sun to its average distance from the Sun. The farther a planet is, the longer its year, and the relationship between distance and time follows a precise mathematical formula. These 3 laws, taken together, describe the motions of the planets with a simple, accurate elegance that no previous system had ever achieved. They fit the data. They required no epicycles, no complicated wheels within wheels. They were true. But Kepler could not explain why the planets moved in ellipses. He could describe the motion, but he could not say what force caused it. He speculated about a kind of magnetic force from the Sun, but he did not have the mathematical tools to work it out. That explanation would have to wait for another mind, one that would build on Kepler's laws and unite them with a universal principle that governed both the fall of an apple and the orbit of the moon. That mind belonged to Isaac Newton. Newton was born in England in the year 1642, the same year Galileo died. He grew up on a farm, went to Cambridge University, and became one of the most powerful mathematical minds in history. In the year 1687, he published a book called the Principia Mathematica, or simply the Principia. In it, he laid out his 3 laws of motion and his law of universal gravitation. The law of gravitation is a simple idea, simply stated. Every object with mass attracts every other object with mass. The strength of the attraction depends on the masses of the objects and the distance between them. The larger the masses, the stronger the pull. The greater the distance, the weaker the pull. This single force, gravity, is what holds us to the ground. It is what holds the moon in its orbit around the Earth. It is what holds the Earth and the other planets in their elliptical orbits around the Sun. The same force that pulls an apple from a tree. A story that may or may not be literally true, but which captures a deep truth, is the force that guides the planets. Newton's mathematics showed that Kepler's 3 laws of planetary motion could be derived directly from the law of gravity. The ellipses, the varying speeds, the relationship between distance and year length, all of it fell out of the mathematics naturally. The why had been found. Gravity was the invisible cord that held the solar system together. Newton did not stop with theory. He also contributed to the practical side of astronomy. He designed and built a new kind of telescope, one that used a curved mirror instead of a lens to gather and focus light. Lens-based telescopes, like Galileo's, suffer from a problem called chromatic aberration. Different colors of light bend differently as they pass through the glass, creating a blurry image with colored fringes. A mirror, however, reflects all colors equally. Newton's reflecting telescope produced a sharper, clearer image, and it could be made much larger than a lens telescope without the same optical problems. The reflecting telescope became the standard design for large astronomical instruments, and it remains so to this day. The great observatories of the modern world, the ones we will come to later in our story, use mirrors of enormous size, all descended from Newton's first small, polished metal mirror. So the work of Kepler and Newton completed the task that Copernicus had started. The sun was at the center, the orbits were elliptical, and the force that drove it all was gravity, a universal law that applied everywhere. The solar system had a shape and a mechanism. The patient observations of Tycho Brahe, the mathematical persistence of Johannes Kepler, and the profound insight of Isaac Newton had, together, given humanity a new and solid understanding of our place in the cosmos. We were on a planet, moving according to precise and knowable laws, around a star that was itself just one among many. The quiet work of watching the sky had become a true science, grounded in measurement and mathematics. And with that foundation secure, the next generations would turn their attention outward, building bigger telescopes, seeing deeper into the sky, and beginning to ask what those faint, mysterious patches of light might be. The known universe was about to expand again, gently, slowly, as it always does. The known universe was about to expand again, gently, slowly, as it always does. With the mathematical foundations of astronomy now secure, the next generations turned their attention outward, building bigger telescopes, seeing deeper into the sky, and beginning to ask what those faint, mysterious patches of light might be. The 18th and 19th centuries were an age of great instruments and great observers, an age when the solar system grew larger and the universe beyond it began, just barely, to reveal its true depth. This was the era of bigger telescopes and wider skies. The story of this era begins, in many ways, with a musician. William Herschel was born in the year 1738 in Hanover, in what is now Germany. His father was a musician in the Hanoverian army, and William followed him into the profession, playing the oboe and the violin. As a young man, he moved to England, where he worked as a music teacher, a conductor, and a composer. He wrote symphonies and concertos. He gave music lessons to the wealthy families of Bath, a fashionable spa city. But William Herschel had a hobby, and that hobby slowly consumed his life. He was fascinated by astronomy. He began by reading books on the subject, learning the constellations, understanding the mathematics, and then he decided he needed to see the sky for himself. He needed a telescope. Telescopes in those days were expensive, and Herschel was not a wealthy man, so he decided to build his own. He taught himself the art of grinding and polishing mirrors, an incredibly delicate and time-consuming process. He worked with his sister, Caroline Herschel, who would become a remarkable astronomer in her own right. Together, in their house in Bath, they would spend hours polishing the metal mirrors, a process that required constant, steady motion. Caroline would often read aloud to her brother while he worked, or feed him spoonfuls of food so he would not have to stop and interrupt the delicate polishing rhythm. They built larger and larger telescopes, each one more powerful than the last. The mirrors were made of speculum metal, a shiny alloy of copper and tin, which tarnished quickly and needed regular repolishing. The tubes were made of wood and iron. The mounting frames were complex and carefully balanced. Herschel's telescopes were not the small spyglasses of Galileo. They were enormous instruments, some of them 40 feet long, with mirrors up to 4 feet in diameter. They were the most powerful telescopes in the world at that time. On the night of March 13th, in the year 1781, William Herschel was conducting a systematic survey of the night sky from his garden in Bath. He was using a 7-foot telescope with a 6-inch mirror, patiently sweeping across the constellations, noting the positions and appearances of stars. In the constellation of Taurus, the bull, he came across a small, faint object that did not look quite like a star. It appeared as a tiny disk, not a sharp point of light. At first, Herschel thought it might be a comet. He watched it over the following nights and saw that it moved slowly against the background stars, confirming that it was a member of the solar system. But as more observations came in, and as astronomers around Europe calculated its orbit, it became clear that this was no comet. It was a planet, a new planet, the first to be discovered in recorded history. The 6 known planets, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, had been known since ancient times. Now there was a 7th. Herschel wanted to name it Georgium Sidus, George's star, after King George III of England, but the astronomical community eventually settled on the name Uranus, after the Greek god of the sky, continuing the mythological tradition of the other planets. The known solar system had doubled in size. Beyond Saturn, there was Uranus, a cold, blue-green world, taking 84 years to complete one orbit around the Sun. The discovery was a quiet sensation. It showed that the solar system was not a closed set of ancient knowledge. There were new things to find out there. The sky still held surprises. William Herschel did not stop with the discovery of Uranus. He continued his systematic surveys, now with the support of King George, who appointed him the king's astronomer with a small salary. He moved to Slough, near Windsor, where he built his largest telescope, the 40-foot. He and Caroline continued to sweep the skies. William catalogued double stars, pairs of stars that orbit each other, proving that Newton's law of gravity applied far beyond the solar system. He studied the faint, cloudy patches in the sky that astronomers called nebulae. He compiled a catalogue of 2,500 of them. He speculated, with quiet insight, that some of these nebulae might be island universes, vast collections of stars like our own Milky Way, seen from an immense distance. This was a prescient idea, though it would take more than a century to confirm, and throughout all this work, his sister Caroline was at his side, and then increasingly, she was making her own contributions. Caroline Herschel was born in 1750. As a young woman, she had been kept at home, serving as a household helper, her own talents stifled. Her brother rescued her, bringing her to England to work as his assistant. At first, she was simply his helper, polishing mirrors and taking notes. But she learned. She became a skilled observer in her own right. She began sweeping the skies with her own small telescope, a gift from her brother, looking for new objects. She discovered 8 comets, a remarkable number for a single observer using a small instrument. She also cross-referenced and corrected the great star catalogues of the past, especially the work of John Flamsteed, the first Astronomer Royal of England. Her revised catalogue, containing thousands of stars with corrected positions, was a major contribution to astronomy. She became the first woman in history to receive a salary for her scientific work, when King George appointed her as William's assistant with a small annual stipend. She lived to be 98 years old, a quiet, determined figure who carved out a place for herself in a world that had little room for women of science. Her comet discoveries and her careful catalogue work are part of the permanent fabric of astronomy. The Herschel name, which we associate with planets and nebulae and deep surveys of the sky, belongs to both of them, brother and sister, working together and then apart, under the same wide night. As telescopes grew larger and more sophisticated throughout the 1800s, the faint, cloudy patches that Herschel had catalogued became objects of intense study. Some of these nebulae turned out to be clusters of stars, thousands or even hundreds of thousands of stars, held together by gravity. Others were clouds of glowing gas, stellar nurseries where new stars were being born, or the expanding shells of dead stars. The universe was not just a collection of individual stars. It was a rich landscape of different kinds of objects, each with its own life cycle and its own story. The telescope had revealed a new level of complexity in the sky. And then, in the 19th century, astronomers found a new way to study the stars. They found a way to ask not just where the stars are and how they move, but what they are made of. This was the invention of spectroscopy. The word comes from the word spectrum, which means a band of colors. The idea is simple. When you pass a beam of sunlight through a glass prism, the light spreads out into a rainbow of colors, from deep red at one end through orange, yellow, green, blue, and violet at the other. This is the visible spectrum. Isaac Newton had done this experiment in his Cambridge rooms in the 1660s, but it was not until the early 1800s that scientists began to examine the spectrum of the sun and other stars very closely, using narrow slits and precision prisms to create a detailed, spread-out band of light. And when they did, they noticed something strange. The smooth rainbow of the solar spectrum was crossed by a series of dark lines, fine gaps where the light was missing. A German optician named Joseph von Fraunhofer mapped hundreds of these dark lines in the solar spectrum in the 18-teens and gave the most prominent ones letter designations that are still used today. He also looked at other stars and found that their dark lines were similar to the sun's, but not identical. Each star had its own unique pattern of dark lines, like a fingerprint. The meaning of these lines was discovered later in the century by Gustav Kirchhoff and Robert Bunsen, working in Germany. They found that every chemical element, when heated to incandescence, emits light at very specific wavelengths, producing a pattern of bright, colored lines. And when white light passes through a cooler gas of the same element, the gas absorbs light at those exact same wavelengths, leaving dark lines in the spectrum. The dark lines in the solar spectrum were absorption lines, caused by cooler gases in the sun's outer atmosphere, absorbing light from the hotter interior. And the pattern of lines revealed the chemical elements present in those gases. This was a revelation. It meant that you could learn what the stars are made of just by looking at their light. No need to travel to them, no need to bring back a sample. The light itself carried the information, encoded in the dark lines of the spectrum. Astronomers began to attach spectroscopes to their telescopes, spreading the light of stars and nebulae into detailed rainbow bands. They found that the stars are made mostly of hydrogen and helium, the simplest and most abundant elements. They found traces of iron, calcium, sodium, and other familiar elements. The universe, it turned out, is made of the same stuff as the Earth. The same chemical elements, governed by the same physical laws, exist everywhere. Spectroscopy turned astronomy into a true physical science, a branch of physics, and it would only grow more powerful as the centuries passed. It allowed astronomers to measure the temperatures of stars, their speeds toward or away from us, their compositions, even their ages. All of this from a careful, patient study of light. Another quiet transformation was taking place in the way astronomers recorded their observations. Since the time of Galileo, and for thousands of years before him, the only way to record what the sky looked like was to draw it. Astronomers would sit at the eyepiece of their telescopes, squinting in the dark, carefully sketching the positions of stars, the shape of a nebula, the shadows on the lunar surface. These drawings were often beautiful, works of art as well as science, but they were subjective. They depended on the skill and the eye of the observer. Two different astronomers looking at the same nebula might produce two slightly different drawings. The search was on for a more objective method, a way to let the sky record itself. And that method arrived in the form of photography. In the middle decades of the 1900s, astronomers began to attach cameras to their telescopes, replacing the human eye with a glass photographic plate coated with light-sensitive chemicals. A photographic plate had a great advantage over the eye. It could accumulate light over time. The human eye sees in real time. A faint object either registers or it does not. But a photographic plate, exposed to the sky for minutes or hours, could gather light continuously, building up an image of objects far too faint for any human eye to see. The first photograph of a star, Vega, was taken in 1850. The first detailed photograph of the moon followed soon after. By the end of the century, photography had become a standard tool of astronomy. Nebulae that had been described in words and drawn in sketches could now be seen in their true, detailed shapes. Star clusters could be counted accurately. The great photographic sky surveys of the late 19th and early 20th centuries created a permanent, objective record of the sky, a baseline against which future generations could measure change. Photography did not replace the human observer entirely. The astronomer still had to aim the telescope, adjust the focus, guide the instrument carefully as the Earth turned during a long exposure. But the eye was no longer the sole recorder of the light. The light now recorded itself. So the era of bigger telescopes and wider skies was an era of expansion on many fronts. The solar system grew beyond the ancient planets. The catalogues of nebulae and star clusters grew into the thousands. The light of the stars was spread into spectra, revealing their chemical secrets. And the photographic plate began to capture images that no eye would ever see directly. The universe was becoming richer, more detailed, more physically real. The faint patches of light that William and Caroline Herschel had catalogued were now being studied with new tools and new techniques. Some of them were clusters of stars within our own galaxy. Some were glowing clouds of gas. And some were something else entirely, something that would force the next great expansion of the known universe. The question of what those faint spiral nebulae really were, whether they were nearby clouds or distant galaxies in their own right, was beginning to take shape. It was a question that would not be answered until the early decades of the 20th century, when a new generation of astronomers, using even larger telescopes and the very latest tools, would finally see the answer, and in doing so, would reveal a universe far, far larger than anyone had imagined. The question of what those faint spiral nebulae really were, whether they were nearby clouds or distant galaxies in their own right, was beginning to take shape. It was a question that would not be answered until the early decades of the 20th century, when a new generation of astronomers, using even larger telescopes and the very latest tools, would finally see the answer. And in doing so, they would reveal a universe far, far larger than anyone had imagined. This was the moment when the known universe expanded from a single galaxy, our own Milky Way, to a vast ocean of galaxies stretching out in every direction, each one containing billions of stars. It was a quiet but profound reshaping of our place in the cosmos. At the beginning of the 20th century, most astronomers believed that the Milky Way galaxy was the entire universe. The Milky Way, that broad band of light we see crossing the night sky, is our home galaxy, a vast, flattened disk of stars, gas, and dust. Our Sun is just one of those stars, located about 2/3 of the way out from the center. The Milky Way was known to be large, though its exact size was still being debated. But was there anything beyond it? That was the question. The telescopes of the time showed many faint, cloudy patches in the sky, the nebulae. Some of these were clearly within our galaxy, like the glowing gas clouds in the constellation of Orion. But others had a distinct spiral shape, like a pinwheel seen from above or at an angle. The most famous of these was the Great Nebula in Andromeda, the same little cloud that Al-Sufi had noted in his Book of Fixed Stars nearly 1,000 years earlier. Through a large telescope it appeared as a faint, elongated smudge of light with a bright center and hints of spiral arms. Was this a relatively small, nearby object within our own galaxy? Perhaps a new solar system in the process of forming, as some astronomers thought? Or was it a separate galaxy, an island universe, vast and distant, like our own Milky Way, but seen from far, far away? The debate was serious and long-lasting. In the year 1920, two prominent astronomers, Harlow Shapley and Heber Curtis, held a formal debate on the subject before the National Academy of Sciences in Washington, D.C. The event is now known as the Great Debate, though it was not a contest with a clear winner at the time. Shapley argued that the spiral nebulae were part of our own galaxy, and that the Milky Way was essentially the whole universe. He had done important work measuring the size of the Milky Way, showing it was much larger than previously thought, and he believed it encompassed everything. Curtis argued that the spiral nebulae were separate galaxies, island universes in their own right, located at immense distances. Both men made good points. Both relied on the best evidence available. But the evidence was not yet conclusive. The debate could not be settled by argument alone. It needed new observations, new data, and a new way of measuring distances across the vast, dark spaces of the sky. The tool that would solve this puzzle was a particular kind of star, a type of star that varies in brightness in a very regular and predictable way. These stars are called Cepheid variables. The first such star, Delta Cephei, was discovered in the constellation Cepheus in the late 18th century. Astronomers noticed that this star would grow brighter and then fainter in a steady, repeating cycle. It was not a binary star, two stars eclipsing each other. The variation was happening inside the star itself. Cepheid variables are unstable stars that pulsate, expanding and contracting in a regular rhythm. And crucially, the length of the pulsation cycle is directly related to the star's true intrinsic brightness. The longer the period, the brighter the star. This is a simple, powerful relationship. If you can measure the period of a Cepheid variable, the time it takes to go through one full cycle of brightening and dimming, you know how bright the star really is. And if you know how bright the star really is, and you compare that to how bright it appears to be in the sky, you can calculate its distance. The dimmer it appears, the farther away it must be. This is the principle of the standard candle, an object whose true brightness is known, so that its apparent brightness reveals its distance. The astronomer who used Cepheid variables to settle the great debate was Edwin Hubble. Hubble was born in the year 1889 in Marshfield, Missouri. He was a tall, athletic man, a boxer in his youth, who had studied law as well as science. But his true love was astronomy. After serving in the First World War, he joined the staff of the Mount Wilson Observatory in California, home to the largest telescope in the world at that time, the Hooker telescope, which had a mirror 100 inches in diameter, more than 8 feet across. This telescope, perched on a mountain peak above the Los Angeles basin, was the most powerful tool for looking deep into the sky that had ever been built. Hubble pointed it at the Andromeda Nebula and began a careful, patient search. He took long exposure photographs, night after night, of the faint spiral arms. And in the year 1923, he found what he was looking for. On a photographic plate, he identified a Cepheid variable star in Andromeda. He measured its period of variation. He calculated its distance. And the number he got was staggering. The star, and therefore the nebula it was in, was about 900,000 light-years away. That was far, far outside the boundaries of our own Milky Way galaxy, which Shapley himself had shown to be about 100,000 light-years across. Andromeda was a separate galaxy, an island universe, a vast collection of stars in its own right, comparable in size to our own Milky Way. Hubble's discovery was announced in the year 1925, and it effectively ended the Great Debate. The universe was not one galaxy. It was at least two, and as telescopes improved and more Cepheids were found in other spiral nebulae, it became clear that the universe was not two galaxies either. It was many. It was countless. The spiral nebulae were not small, nearby clouds. They were distant galaxies, each one containing hundreds of billions of stars. The known universe had expanded by an almost unimaginable factor, from one galaxy to a universe full of galaxies. Al-Sufi's little cloud in Andromeda was a twin to our own Milky Way, a swirling disk of stars seen from a distance of more than 2 million light-years, a number later revised from Hubble's initial estimate. The light that formed his image on the photographic plate had left Andromeda more than 2 million years ago, long before there were any humans on Earth to see it. The scale of both space and time had grown vast and quiet and deep. But Hubble was not finished. He continued to study the galaxies, measuring their distances and also their speeds. The speed of a galaxy can be measured using spectroscopy, the same technique that reveals the chemical composition of stars. When a light source moves toward an observer, its light waves are compressed, shifting the spectrum toward the blue end. When a light source moves away, its light waves are stretched, shifting the spectrum toward the red end. This is the Doppler effect, named after the Austrian physicist Christian Doppler, and it works for light just as it works for sound. Think of the way a siren on a passing ambulance sounds higher as it approaches and lower as it recedes. Light does the same thing. By measuring the shift in the spectral lines of a galaxy, astronomers can tell how fast it is moving toward or away from us. Hubble, working with his colleague Milton Humason, measured the spectral shifts of many galaxies, and what they found was remarkable. Most galaxies are moving away from us. The farther away a galaxy is, the faster it is receding. This relationship, now called Hubble's law, suggests that the universe is expanding. The galaxies are not simply flying apart through a fixed, static space. Space itself is stretching, carrying the galaxies along with it like raisins in a rising loaf of bread. The discovery of the expanding universe was published in the year 1929. It was one of the most profound findings in the history of science. The universe had a history. It had a direction of change. If it is expanding now, then in the past, it must have been smaller and denser. This led, over the following decades, to the development of the Big Bang theory, the idea that the universe began in an extremely hot, dense state and has been expanding and cooling ever since. The universe was not eternal and unchanging, as many scientists had assumed. It was dynamic, it had a beginning, and it was far, far older than anyone had previously calculated, with the best current estimate being about 13.8 billion years. Underlying all of this work, providing the theoretical framework for understanding the expanding universe, was a new theory of gravity and space-time. In the year 1915, Albert Einstein had published his general theory of relativity. It is a dense and complex mathematical theory, but its core idea can be stated simply. Gravity is not a force that pulls objects across empty space, as Newton had described it. Gravity is the bending, the curving, of space and time themselves by the presence of mass and energy. A massive object like the sun or a planet or a galaxy actually curves the space-time around it. Other objects, moving through that curved space-time, follow paths that we perceive as the pull of gravity. The planets orbit the sun not because they are pulled by an invisible cord, but because they are moving along the curves in space-time that the sun's mass creates. This theory explains some small puzzles that Newtonian gravity could not, such as a tiny shift in the orbit of Mercury, and it made predictions that could be tested. During a solar eclipse in 1919, astronomers measured the positions of stars near the sun's edge and found that their light was bent by the sun's gravity, exactly as Einstein's theory predicted. General relativity also provided the mathematical tools for describing the universe as a whole. It allowed cosmologists to model the expansion of space, the evolution of the early universe, and the possible fates of the cosmos far in the future. So, in the span of just a few decades, the known universe expanded from a single galaxy to countless galaxies. Our Milky Way, which had once seemed to be everything, became just one among billions. The universe was not static and eternal. It was expanding, evolving, stretching its own fabric as it grew. The telescope, combined with spectroscopy and the new physics of general relativity, had revealed a cosmos of staggering scale and profound mystery. The quiet, patient work of measuring the light from distant stars had shown us that we live on a small planet, orbiting a fairly ordinary star, on the outskirts of one galaxy among many. There was no center to the universe, or rather every point was equally a center, with galaxies receding in every direction. The perspective had shifted again, gently and irrevocably. The sky that our ancestors had watched for thousands of years was not a dome over a flat Earth. It was not the turning spheres of Ptolemy. It was not even the single galaxy that the Herschels had begun to map. It was a vast, deep, expanding ocean of galaxies, stretching out into a darkness that we were only just beginning to explore. And the next step, the next great leap, would take us off the surface of the Earth entirely, into space itself. To look at the sky not through the blur of our atmosphere, but from the clear, cold vantage of orbit. And the next step, the next great leap, would take us off the surface of the Earth entirely, into space itself, to look at the sky not through the blur of our atmosphere, but from the clear, cold vantage of orbit. This was the space age. It began not with a telescope, but with a small, polished metal sphere, not much larger than a beach ball, that circled the Earth and beeped. That sphere was called Sputnik. The word simply means satellite, or fellow traveler in Russian. It was launched on October 4th in the year 1957 from the Baikonur Cosmodrome in what is now Kazakhstan. The Soviet Union, which no longer exists as a country, was the first to place an artificial object into orbit around the Earth. Sputnik was simple. It had a radio transmitter and batteries. It sent out a steady, rhythmic beep that could be picked up by receivers on the ground. For 21 days, that small beep was heard around the world. Then the batteries died. Sputnik continued to circle the Earth in silence, a small, bright dot moving across the sky at dawn and dusk, until its orbit decayed, and it burned up in the atmosphere a few months later. But its legacy was immense. It proved that human beings could put an object into space. The barrier that had held us to the surface of our planet since the beginning of our existence had been broken. The sky was no longer something we could only look at. It was a place we could go. The launch of Sputnik was quiet in its physical form, a small sphere and a faint beep, but it marked the beginning of a new era. It set off a wave of investment in science and technology, a quiet but intense push to explore what lay beyond our atmosphere. The United States soon launched its own satellites, and then, just a few years later, human beings followed the machines. In the year 1961, the Soviet cosmonaut Yuri Gagarin became the first human being to orbit the Earth. He was in space for just 108 minutes. But in those minutes, he saw the Earth from a perspective no human had ever seen before. The entire planet, a blue and white sphere, suspended in the blackness of space. The view that had been imagined for centuries, that had been theorized by astronomers and painted by artists, was now seen by human eyes. Then came the moon. The moon had been the object of study for thousands of years. It had been mapped by Galileo. It had been measured and photographed, but no one had ever touched it. In the 1960s, both the Soviet Union and the United States sent robotic probes to the moon, to crash into it, to orbit it, to land softly on its surface, and send back pictures. And then, in the year 1969, on July 20th, two human beings stepped out of a spindly-legged spacecraft called the Lunar Module and stood on the surface of another world. Their names were Neil Armstrong and Buzz Aldrin. Armstrong's words as he stepped onto the dusty gray surface, "One small step for a man, one giant leap for mankind," were heard by millions of people on Earth, a quiet, crackling transmission from 250,000 miles away. The Apollo 11 mission and the 5 successful moon landings that followed it brought back more than 800 pounds of lunar rock and soil. For the first time, astronomers could hold pieces of another world in their hands and study them in their laboratories. The rocks were ancient, billions of years old, and they told a story of a moon formed from the debris of a giant impact early in the Earth's history. The old dream of touching the sky had become real. The moon was a place, with footprints and flags and a small, silent plaque that said, "We came in peace for all mankind." The space age did not only send humans into the void, it also sent telescopes, and that, in many ways, was an even greater leap for astronomy. For all their growing power, the great telescopes on the ground had always faced a fundamental limitation. They had to look through the Earth's atmosphere. The atmosphere is the blanket of air that wraps our planet, and it is essential for life. It gives us air to breathe. It protects us from harmful radiation. But for an astronomer, the atmosphere is a problem. It blurs the light from stars. It makes stars twinkle, a beautiful sight to the naked eye, but a frustrating one for a telescope trying to take a sharp image. Even worse, the atmosphere blocks most of the light that the universe sends our way. Our eyes see visible light, the rainbow of colors from red to violet. But there is a much broader spectrum of light that exists beyond what our eyes can see. There is infrared light, which we feel as heat. There is ultraviolet light, which gives us sunburn. There are X-rays and gamma rays, which carry enormous energy. Much of this light, especially X-rays, gamma rays, and most ultraviolet and infrared, is blocked by the atmosphere. It never reaches the ground. So an astronomer on the ground is like someone trying to understand a symphony by listening through a keyhole. You can hear parts of it, but the full richness is lost. By putting telescopes into space, above the atmosphere, astronomers could see the universe in its full, unfiltered glory. The first space telescopes were small, simple instruments, launched in the 1960s and 70s. They began to map the sky in X-rays and ultraviolet light, revealing a universe that was far more violent and energetic than anyone had expected. They found X-rays streaming from the hot gas swirling around black holes. They found ultraviolet light from young, massive stars. They found a diffuse background of X-rays and gamma rays that seemed to come from all directions, the echoes of ancient, powerful events. The sky, seen in these new kinds of light, was not a calm, quiet field of twinkling stars. It was a dynamic, seething, explosive place, full of energy and change, and we were only just beginning to see it. The most famous of the space telescopes, the one that has done perhaps more than any other to bring the beauty of the universe to the public eye, was launched in 1990. It was named the Hubble Space Telescope, after Edwin Hubble, the astronomer who had shown us the expanding universe. The Hubble telescope was a joint project of the American Space Agency, NASA, and the European Space Agency. It had a mirror just over 7 feet and 10 inches in diameter, not particularly large by ground-based standards. But in space, above the distorting atmosphere, that modest mirror could see with a clarity and depth that no ground telescope could match. The launch of Hubble was a triumph of engineering and planning, but it was soon followed by a quiet crisis. When the first images were taken, they were blurry. The mirror had been ground to the wrong shape, off by a tiny amount, just a fraction of the width of a human hair. The telescope, which had cost billions of dollars and years of work, was not working as planned. The disappointment was deep and quiet. But the story of Hubble is also a story of patient repair. Because Hubble was in orbit, it was designed to be serviced by astronauts. In 1993, a team of astronauts flew to the telescope in the space shuttle. They captured it with the shuttle's robotic arm. They installed new instruments that corrected the flaw in the mirror, working in bulky spacesuits in the cold vacuum of space. When the first corrected images were beamed down to Earth, they were breathtaking, sharp, deep, filled with detail. The fix had worked. Hubble began to fulfill its promise, and it has been doing so ever since, with several more servicing missions over the years to replace aging parts and install new, more sensitive instruments. The images from Hubble have become part of our shared visual culture. The towering pillars of gas and dust in the Eagle Nebula, called the Pillars of Creation, where new stars are being born. The Hubble Deep Field, a tiny patch of sky, no larger than a grain of sand, held at arm's length, in which Hubble stared for many hours and revealed thousands of distant galaxies, stretching back to the early universe. Hubble has measured the expansion rate of the universe more precisely than ever before. It has watched the changing seasons on other planets in our solar system. It has detected the faint atmospheres of planets orbiting distant stars. It has seen the echoes of supernovae, the violent deaths of massive stars, in galaxies millions of light-years away. Hubble, for all its early troubles, became one of the most productive scientific instruments in history. It showed us, with quiet, persistent clarity, that the universe is beautiful beyond our imagining, and that its beauty is built on physical laws we can study and understand. And Hubble was not alone. Other space telescopes were launched, each designed to see a different kind of light. The Chandra X-ray Observatory, launched in 1999, sees the hot, energetic universe. The Spitzer Space Telescope, launched in 2003, saw the infrared universe, the cool clouds of dust where planets form, the warm glow of distant galaxies. These telescopes and many others worked together with Hubble to build a multi-wavelength picture of the cosmos, a view that spanned from the deepest radio waves to the highest energy gamma rays. The universe was no longer just visible. It was audible, tangible, in wavelengths we could not see with our eyes but could detect with our instruments. The space age also saw the launch of robotic probes to the other planets of our solar system. These were not telescopes, exactly. They were explorers. They flew past planets, sending back images of worlds that had previously been only points of light or fuzzy disks. Mariner and Viking went to Mars and revealed a cold, dry desert world with ancient riverbeds and towering volcanoes. Pioneer and Voyager went to Jupiter and Saturn and beyond. Voyager 1 and Voyager 2, launched in 1977, flew past Jupiter and Saturn. Then Voyager 2 went on to Uranus and Neptune, the first and only probe to visit those distant worlds. The images they sent back showed planets of stunning beauty and variety. Jupiter, with its swirling clouds and its great red spot, a storm larger than the Earth that has been raging for centuries. Saturn, with its delicate, intricate rings, made of countless particles of ice and rock. Uranus, tipped on its side, its rings and moons orbiting at right angles to the plane of the solar system. Neptune, a deep, vivid blue, with winds that are the fastest in the solar system. And then, the Voyagers kept going. They passed the orbit of Pluto. They entered the realm of interstellar space. Voyager 1, still transmitting a faint signal back to Earth, is now the most distant human-made object in existence, more than 14 billion miles from home. On board, each Voyager carries a golden record, a phonograph record with sounds and images from Earth, a message in a bottle cast into the cosmic ocean, a quiet greeting from our small planet to whatever might be out there. The space age has been, in the long sweep of our story, very brief. Sputnik was launched only about 70 years ago, a mere heartbeat in the history of astronomy, and yet, in that short time, we have stepped off our planet and onto another world. We have sent our eyes and our ears across the solar system and out into the galaxy. We have built telescopes that see the universe in ways our ancestors could never have dreamed. We have, in a very real sense, become a spacefaring species. The sky is no longer a distant, untouchable realm. It is our environment. It is our home. And as we look deeper, with ever more powerful instruments, we continue to find that the universe is larger, stranger, and more beautiful than we had ever imagined. The story of astronomy, which began with a person standing in a dark field and looking up, has now taken us to the edge of the solar system and beyond. And still, the questions continue. What is out there in the deep dark? What is the universe made of? How did it begin? How will it end? The answers are still unfolding, slowly, gently, as they always have. And the next chapter is already being written, with a new telescope, the most powerful ever built, peering back to the very dawn of time. And the next chapter is already being written, with a new telescope, the most powerful ever built, peering back to the very dawn of time. That telescope is the James Webb Space Telescope. It was launched on Christmas Day in the year 2021, after decades of planning and design and careful testing. It is the successor to the Hubble Space Telescope, but it is not simply a bigger, better version of the same thing. It is a different kind of instrument entirely, designed to see a different kind of light and to answer different kinds of questions. If Hubble gave us the visible universe in stunning detail, Webb was built to see the infrared universe, the heat glow of the oldest, coldest, and most distant objects in the cosmos. The James Webb Space Telescope is a marvel of quiet engineering. Its main mirror is made up of 18 hexagonal segments, each one coated in a thin layer of gold. The gold gives the mirror a beautiful warm hue, but it was chosen for a practical reason. Gold reflects infrared light very well. The mirror segments are arranged in a honeycomb pattern, and together they form a collecting area more than 21 feet across, making it the largest mirror ever launched into space. The mirror is so large that it had to be folded up to fit inside the rocket that carried it into space. Once in space, it unfolded itself, slowly and carefully, in a complex sequence of deployments that took several weeks. Everything had to work perfectly. There was no crew of astronauts to fix it if something went wrong, as there had been with Hubble. The telescope was on its own, 1,000,000 miles from Earth, far beyond the reach of any repair mission. The reason the James Webb Space Telescope was sent so far away is simple and important. It is designed to see infrared light, which is a kind of light that we feel as heat. Everything that is warm, including the Earth itself and the telescope's own instruments, gives off infrared light. To see the faint infrared light from the most distant galaxies, the telescope has to be kept incredibly cold. So Webb was sent not into orbit around the Earth, but to a special location called a Lagrange point, a point in space where the gravity of the Earth and the gravity of the Sun balance each other. At this point, the telescope can sit in a stable position, using a small amount of fuel to stay in place. More importantly, it can deploy a giant sun shield, a layered sheet of thin material, the size of a tennis court, that blocks the light and heat from the Sun, the Earth, and the Moon. Behind that shield, the telescope's instruments are cooled to temperatures only a few degrees above absolute zero, the coldest possible temperature. This extreme cold allows the telescope to see the faint, ancient infrared light that has been traveling across the universe for billions of years. What the James Webb Space Telescope sees is light that has been stretched by the expansion of the universe. As we learned earlier, the universe is expanding, and as light travels through expanding space, its wavelength gets stretched. Visible light from very distant galaxies is stretched into infrared light by the time it reaches us. This is called cosmological redshift. The farther away a galaxy is, the more its light is redshifted. To see the very first galaxies that formed after the Big Bang, you need an infrared telescope, and you need it to be very large and very cold. The James Webb Space Telescope was designed to see exactly those galaxies, the first generation of stars and galaxies that lit up the universe more than 13 billion years ago. The light from those galaxies has been traveling to us for almost the entire history of the universe. When we look at them, we are looking directly into the past, seeing the universe as it was when it was just a few 100 million years old. The young universe was a different place, full of hot, massive stars, chaotic galactic mergers, and the first seeds of the structure we see around us today. Webb is showing us that early era with a clarity that no previous telescope has ever achieved. And the images that have come back from Webb, even in just its first few years of operation, are quietly staggering. The first deep field image, released in July of 2022, showed a patch of sky no larger than a grain of sand held at arm's length. And in that tiny patch, there were thousands of galaxies. Some of them are familiar spirals and ellipticals, but many of them are strange, distorted smears of light, warped by the gravity of intervening galaxy clusters. This warping is called gravitational lensing, and it is a beautiful, gentle effect predicted by Einstein's general theory of relativity. A massive galaxy cluster can act like a lens, bending and magnifying the light from galaxies behind it. Webb sees these arcs and smears of light, and it uses them to study galaxies that would otherwise be too faint and too distant to see. The images are not just scientifically valuable, they are deeply beautiful. They show a universe teeming with galaxies of every shape and color, stretching back to a time just a few 100 million years after the beginning. The deep field is not just a photograph. It is a time machine, a history book written in light, and every faint smudge in the image is a galaxy of billions of stars. But for all that we have learned, for all that the James Webb Space Telescope and all the other great instruments are telling us, there remains a vast, quiet space of not knowing. And that is where we find ourselves now, at the end of this long, slow walk through the history of astronomy. We have come so far, from the first person who looked up at a dark sky and wondered, to the great stone circles, to the clay tablets of Babylon, to the polished mirrors of Herschel, to the space telescopes that peer back to the dawn of time. And yet, when we add up everything we know, it turns out that most of the universe is still a mystery. The stars and galaxies, the glowing nebulae, the planets and moons, all of the matter that we can see with our telescopes, makes up only a small fraction of what the universe contains. The rest is dark. There are two great, quiet mysteries in modern cosmology, and they go by the names dark matter and dark energy. We do not know what they are, we cannot see them directly, we can only see their effects, the gentle pull they exert on the things we can see. Dark matter is a kind of invisible material that does not emit, absorb, or reflect any light. We know it is there because of the way galaxies rotate. The stars at the outer edges of spiral galaxies move much faster than they should, if only the visible matter were holding them in place. There must be an additional source of gravity, a vast, diffuse halo of unseen matter surrounding and permeating the galaxy. This dark matter outweighs the visible matter by about 5 to 1. It is the invisible scaffolding upon which the visible universe is built. The galaxies we see are just the bright tips of a much larger, darker structure. Scientists have searched for dark matter particles in deep underground laboratories, using incredibly sensitive detectors. They have searched for signs of dark matter in the collisions of particles at the Large Hadron Collider. So far, they have found nothing. The nature of dark matter remains one of the great open questions in all of science. We know it is there. We can map its distribution using gravitational lensing, but we do not know what it is made of. It is a quiet, persistent reminder that the universe is not yet fully known. And then there is dark energy. In the late 1990s, 2 independent teams of astronomers were studying distant supernovae, the explosions of dying stars, to measure the expansion rate of the universe over time. They expected to find that the expansion was slowing down, gradually coasting to a stop under the pull of gravity from all the matter in the cosmos. Instead, they found the opposite. The expansion of the universe is speeding up. The galaxies are moving away from each other faster and faster as time goes on. Something is pushing the universe apart, counteracting the pull of gravity on the largest scales. That something is what we call dark energy, and it is the dominant component of the universe, making up about 70% of the total energy content of the cosmos. We have no satisfactory explanation for what dark energy is. It may be a property of space itself, a constant energy present in every cubic centimeter of vacuum. It may be something more dynamic, a field that changes over time. We simply do not know. The discovery that the universe's expansion is accelerating was a quiet, profound shock to cosmology. It meant that the fate of the universe, far in the future, is not a slow collapse back into a hot, dense state, but a continued, accelerating expansion into a cold, dark, empty future. The universe will not end in a bang. It will simply grow colder and darker, the galaxies moving ever farther apart, the stars eventually burning out, the matter itself slowly decaying over unimaginable stretches of time. This is not a cause for alarm. It is a cause for quiet contemplation. The timescales involved are so vast that they are beyond any human measure. The universe has billions and billions of years ahead of it, and the story of life and intelligence and the slow, patient watching of the sky is still, in cosmic terms, just beginning. So here we are, at the end of our long, slow walk. The story of astronomy is the story of questions asked softly, over centuries. What are those lights? How do they move? What is our place among them? The answers have come slowly, piece by piece, and each answer has only led to deeper questions. The universe we now know is vast beyond our imagining. It is filled with galaxies beyond counting, each one filled with stars beyond counting. It began in a hot, dense state billions of years ago and has been expanding and cooling ever since. It is mostly made of dark matter and dark energy, two things we do not yet understand. Most of the universe remains unmapped and unexplained, and that is simply where current understanding stands. That is not a failure. It is not a problem to be solved with a dramatic revelation. It is just the quiet, open truth. The not knowing is part of the calm. And yet, through all of this, through all the complexity and the mystery and the vastness, there is one thing that has not changed: the simple act of looking up. A person, somewhere, on a night without a moon, stepping away from the low light and tilting their head back. The same sky that the builders of Stonehenge watched, the same stars that the Babylonian scribes recorded on their clay tablets, the same moon that Galileo sketched through his small telescope, the same faint smudge in Andromeda that Al-Sufi noted in his book of fixed stars. The sky is still there, above us, every clear night. It does not demand anything of us. It does not ask us to understand it. It simply is. A vast, quiet, beautiful presence, turning slowly overhead. So as you lie here in the dark, letting your mind drift among the stars, remember that you are part of this long, slow story. You are a sky watcher too. The light that falls on your closed eyelids is the same light that has been traveling for millions and billions of years, crossing the vast spaces between the galaxies, to reach this moment, to reach you. The universe is large and old, and mostly unknown, and that is all right. The questions can wait. The sky will still be there tomorrow night, and the night after that, and for all the nights to come. For now, just rest. Let the quiet turning of the stars carry you, slowly and gently, towards sleep. The story will continue, as it always has, in the patient watching of those who come after us. But for tonight, the watching is done. Just breathe, and let the sky watch over you.